We've crossed oceans, split atoms, and walked on the moon, yet Pluto might as well be on the far side of forever. Proxima Centauri, the nearest star, isn't just far. It's a distance that turns rockets into rounding errors. So what exactly is stopping us? Physics, fuel, fragile bodies, or engineering? And what breakthrough would finally make the impossible a flight plan? In the modern age, space can feel almost navigable. Lines on a map, clean arcs in software, a countdown that ends in triumph. But beyond the last bright planet, the universe stops feeling cinematic and starts feeling contractual. Every kilometre has terms. Pluto sits out there like a quiet promise, a distant world with a name we all learned as children. And Proxima Centauri, our nearest stellar neighbour, hangs in the same sky, close enough to point at, far enough to mock certainty. So why, after a century of rockets and a generation of probes, do these destinations still feel farther away than the edge of imagination? Not in poetry, but in numbers. Numbers that do not negotiate. This film follows the real limits that stand between us and quickly, and between us and within a lifetime. Some of them are familiar: propellant, power, and mass, yet their true force hides in compounding math. Others are less visible until you try to build the mission: the violence of acceleration, the burden of braking, and the silent demand to carry your own survival. We will watch how a fast Pluto mission becomes years, and how even a perfect trajectory can end as a fleeting flyby, unless you can afford to stop. We will step from light hours to light years, where chemical rockets drift from ambitious to absurd, and where every extra fraction of speed turns engineering into infrastructure. Along the way, we will confront the limits that don't fit on mission patches: radiation that accumulates quietly, dust that becomes shrapnel at extreme velocities, and biology that was never designed for decades in a sealed machine. And we will ask the most important question of all: if these journeys are effectively impossible today, what would have to change to make them merely expensive? Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey to answer the question: why reaching Pluto or Proxima Centauri is still impossible. We live in a time when space looks conquered because screens compress it into something that feels manageable. Apollo footprints imply closure, as if a few bootprints can finish a frontier. Voyager's golden record implies permanence, a polished message that seems able to outlast the void. New Horizons at Pluto implies routine progress, a neat headline that makes the outer solar system feel like a scheduled stop. Then the story cuts to what the cameras rarely show: the long dark between targets, where nothing happens quickly. The frame holds on a starfield that barely shifts, and the silence becomes a kind of measurement. In that emptiness, the mind has no landmarks, and time stops feeling like an accessory. It becomes the main character. Our confidence is real, and our achievements are historic, even by the standards of older civilizations. We crossed the first ocean of space to the moon, and we learned to land on another planet with precision. We built machines that survive vacuum, cold, and radiation for decades, while their parts slowly age in deep space. We can point antennas across billions of kilometers and still hear a whisper, pulled from noise by mathematics and patience. Yet distance does not care about our pride, or our headlines, or the way a mission patch looks on a jacket. Space is not impressed by a launch countdown because it has no sense of urgency. It only has scale, and scale turns every plan into a negotiation. The negotiation is not emotional, but we feel it emotionally. The contradiction is emotional and mathematical at once, and it hides inside familiar images. In classrooms and movies, the solar system fits on a page with tidy orbits and evenly spaced labels. In mission control, a trajectory looks like a clean arc, drawn by software that makes complexity appear smooth. In the mind, a planet becomes a destination like a city, because our brains evolved for roads, not orbits. But in physics, space is mostly emptiness, and emptiness is what takes time. The gaps are not decorative, and they do not scale down just because we zoom out. Even gravity, which shapes everything, becomes a faint influence when you're far enough away. The result is a universe that looks close but behaves far. Pluto is not the farthest object, but it marks an edge in our cultural map. It is the last classical planet in the old mnemonic, and the first place that feels truly remote. Proxima Centauri is not a bright star in our sky, but it is the nearest one. It sits 424 light-years away, close enough to tempt ambition and far enough to break it. In a telescope, it is a dim red point in Centaurus easy to overlook. In astrophysics, it is a real sun with storms, magnetic fields, and a complex environment. In our imagination, it is the next porch light on the street. Pluto matters because it is still within our sun's neighbourhood, yet it resists quick travel in a way that surprises people. It is a milestone that proves how slow fast really is once you leave the inner planets. Proxima matters because it is the next neighbourhood entirely, separated by an ocean that has no ships. It is the first step of interstellar civilization, if such a step is possible. To understand why these two targets define our limits, we need a new intuition. We need to stop thinking in kilometres and start thinking in time, because time is what we actually experience. Time is the currency that distance demands, and light sets the exchange rate. Light is not just a speed, it is a limit on cause and effect. The moon is about 1 1/3 light seconds away, which sounds small until you try to work with it. That number means every conversation with an astronaut has a built-in pause, even in the best-case scenario. It also means remote control is never perfectly immediate, which matters for landing, docking, and emergencies. Even at the moon, speed and delay are part of the experience. The sun is about 8 light minutes away, and that distance already makes the solar system feel real. When you see sunlight on Earth, you are seeing the sun as it was 8 minutes ago. A solar flare does not arrive instantly, and neither does a command sent to a spacecraft near the sun. The inner planets sit within light minutes, yet they are not nearby in any human sense. Mars, at its closest, is only a few light minutes away, but at its farthest it is much more. That shifting distance is not a detail. It is a scheduling constraint that shapes launch windows and mission designs. When engineers plan a landing, they plan for a world that is already in the past by the time the signal arrives. The planet you see on a screen is not the planet the rover is touching. Jupiter is roughly tens of light minutes away, depending on where we are in orbit and where it is in its path. Saturn pushes toward more than an hour of light travel at times, and that hour changes how you think. Uranus and Neptune stretch that to multiple light hours, and the delay becomes a working condition. At those distances, a spacecraft is never in immediate contact with Earth. It is always operating with delay, and often with autonomy, because waiting is not a strategy. The Deep Space Network listens with giant dishes, and it listens for tiny power levels. Signals spread out as they travel, thinning like ripples on a pond, and Earth becomes a faint source. Communication is still possible, but it is never casual. Beyond the planets, the sun's influence thins into a boundary we call the heliopause, where the solar wind yields to interstellar space. It is not a wall, but it is a frontier, shaped by pressure and plasma rather than stone. Voyager 1 and Voyager 2 approached it slowly, and their instruments watched the sun's bubble weaken. That boundary is measured in light days, not light hours. The scale shift is subtle on paper and brutal in flight time because paper does not age. A spacecraft ages, and its power supply declines and its heaters struggle. Its instruments drift, and its software becomes a fossil of the year it launched. Deep space is not just far, it is long. Then comes the step that changes everything, because the units stop behaving like bigger versions of themselves. The nearest star is not light days away, and it is not light months away. It is light years away, and that unit is not just bigger. It is a different category of distance, because it multiplies every constraint at once. A light year is the distance light travels in 1 year, and light is the fastest signal we have. In kilometers, it is about 9.46 trillion, a number so large it becomes abstract. If light needs years, then everything slower needs more, and everything heavy becomes a burden. A probe at the speed of our fastest chemical rockets would need tens of thousands of years. Even a probe moving at 1% of light speed needs centuries, and centuries are not a mission timeline. They are a civilizational timeline, full of unknowns that no engineering margin can cover. The problem is not only getting to speed, but also surviving long enough to use it. A fast probe that dies early is not fast in any meaningful sense. Pluto sits at the edge of the classical solar system, and it still took decades to reach in practice. New Horizons launched in 2006 and arrived in 2015, after a gravity assist at Jupiter that stole a little momentum. That was a triumph of navigation, patience, and engineering discipline, executed across a widening gulf. It was also a reminder that our quick missions are measured in years, even before leaving the Sun. The flyby itself was a kind of high-speed whisper, because the window for close observation was brief. Instruments had to work on a tight schedule, scanning and recording while the spacecraft raced past. The images we remember were not broadcast live because the data rate was too low. They were stored, then sent back slowly, packet by packet, over many months. New Horizons did not slow down to orbit Pluto, and that choice was not aesthetic. It flew past because braking costs fuel, and fuel costs mass, and mass costs everything. A flyby is a compromise that buys discovery at the price of permanence. We got images and data, then Pluto receded forever behind the spacecraft. The mission's design was shaped by the same arithmetic that shapes every deep space plan, even when the public sees only the photographs. If you want to stop, you must carry the ability to stop from the beginning. If you carry it from the beginning, you pay for it at launch with a larger rocket. The outer solar system teaches this lesson repeatedly, because it is unforgiving. Proxima Centauri makes that arithmetic feel merciless, because the numbers stop fitting inside intuition. 4.24 light-years is about 40 trillion kilometers, and that is only the nearest neighbor. It is close enough that we can measure its wobble and map its flares, because modern spectroscopy is exquisitely sensitive. It is close enough that we can imagine a probe taking pictures of another sun. It is also far enough that every kilogram, every watt, and every year becomes a barrier. Proxima is a red dwarf, cooler than the Sun, and it can be violently active. Its flares matter because they shape the radiation environment a probe would face near arrival. Even the target is not simple, and that complexity adds to the cost. The central mystery of this documentary is not why we have not tried, because we have tried in many forms. We have tried in proposals, in studies, in dreams, and in budgets that never quite close. We have tried in laboratory experiments that hint at new propulsion, and in paper designs that assume perfect materials. The mystery is why progress in one domain does not translate into reach. Better computers, better materials, and better cameras do not automatically buy speed, even when they transform everything else. The bottleneck is propulsion and energy, and those are governed by physics, not optimism. In the 20th century, we learned to miniaturize electronics and multiply computation. We did not learn to multiply exhaust velocity by the same factor. The first constraint is the rocket equation, which hides inside every launch like a quiet rule. To go faster, you need more change in velocity, and that change is called delta V. To get more delta V, you need more propellant, because rockets carry their reaction mass, but propellant has mass, and mass requires more propellant to push it. The result is exponential growth that punishes ambition, because each improvement demands a larger sacrifice. Add a little payload, and you may need a lot more fuel. Add a little fuel, and you may need a bigger tank, which adds more mass again. The equation is not a suggestion, it is a trap you must design around. Chemical rockets are powerful, and they are the reason we reached orbit at all. Their exhaust velocity is limited by chemistry, because chemical bonds release only so much energy per unit mass. They are good at leaving Earth, and good at reaching nearby worlds with careful planning. They are not designed for sustained high-speed travel across the outer solar system. They are certainly not designed for interstellar flight, because the required delta V is in a different regime. Even if you could launch endlessly, you would still be paying the exponential cost. This is why gravity assist matters so much, and why mission designers treat planets like stepping stones. They are borrowing momentum from orbital motion, because carrying it yourself is too expensive. The second constraint is energy, which sets the price of speed in a way that feels almost unfair. Kinetic energy scales with the square of velocity, which means speed becomes expensive quickly. Doubling speed does not double the energy requirement, it quadruples it. At interstellar speeds, the energy budgets become comparable to national power grids, or beyond. Energy is not just a number on paper, because it must be stored, converted, and managed. A spacecraft must turn energy into thrust, and that conversion has inefficiencies. Heat must be rejected into space, and radiators add mass and complexity. Every watt you generate becomes a thermal problem as well as a propulsion problem. The third constraint is acceleration, which turns speed into lived experience rather than a final statistic. A probe can tolerate high acceleration for short periods, but structures have limits, and components shake loose. Humans have stricter limits, and life support adds mass that compounds every other constraint. If you accelerate gently to protect people, you spend longer accelerating. If you accelerate hard to save time, you risk breaking bodies and machines, And you also increase peak power demands. Acceleration is also a navigation issue, because small errors integrate into large misses over long distances. The faster you go, the less time you have to correct. At interstellar scales, a tiny angular mistake becomes an astronomical miss. The fourth constraint is radiation and the particle environment, which is invisible until it fails you. Outside Earth's magnetic shield, cosmic rays and solar storms become chronic hazards, not occasional events. High-energy particles flip bits in memory, degrade solar panels, and slowly damage sensors. Electronics need shielding and redundancy, which adds mass and power draw. Humans need protection that is heavier still, and heavy means slower, unless you pay the energy price again. Radiation is also a time problem, because dosage accumulates. A longer mission is not just a longer wait, it is more exposure. The outer solar system is cold and dark, but it is also harsh in ways that do not photograph well. The fifth constraint is communication delay, which is not just inconvenient for engineers. Delay changes how missions are controlled, how failures are handled, and how crews feel when they are alone. At Pluto, a radio signal takes hours to cross the gap, so troubleshooting becomes slow motion. At Proxima, it takes more than 4 years one way. A conversation becomes a correspondence, and rescue becomes meaningless, because help cannot arrive in time. Even if you could send instructions instantly, you cannot send hardware instantly. Autonomy stops being a luxury and becomes a requirement, because the spacecraft must make decisions without you. The farther you go, the more you must trust machines to improvise. The sixth constraint is the tyranny of time itself, which is both technical and political. Spacecraft systems age, fuels degrade, and budgets shift with elections and economic cycles. A mission that lasts decades must survive changing institutions and fading expertise as teams retire and knowledge disperses. A mission that lasts centuries must survive civilizations, and that is a different kind of engineering. Time also changes the target, because stars move and environments evolve. Proxima is not fixed in space, and neither is the Sun, and trajectories must account for that motion. Over decades, the sky is stable enough for planning, but over centuries it is not. Even the map is in motion, and that motion adds another layer of uncertainty. These constraints do not act separately, they compound, and compounding is what makes the problem feel like a wall. More shielding means more mass, which means more propellant, which means more mass again. More speed means more energy, which means more power generation, which means more mass and heat. More autonomy means more computing and redundancy, which means more mass and complexity. The loop tightens until the mission collapses under its own requirements, unless you change the underlying assumptions. That is why deep space is not merely an engineering challenge, but a systems challenge. Every subsystem touches every other subsystem, and trade-offs become existential. You do not optimize one variable, you negotiate among all of them. This is why Pluto and Proxima belong in the same opening chapter. Even though one is a dwarf planet and the other is a star, Pluto's are proof that even within the Sun's realm, distance extracts a steep toll. Proxima is the proof that beyond the Sun, the toll becomes something like a border. It is not a line on a map, it is a wall of energy, time, and risk. And yet the temptation remains, because the stakes are not academic and they never were. If we cannot cross these distances, our civilization stays confined to one star system, regardless of how advanced our screens look. We can explore with robots, but we cannot spread, and we cannot easily escape planetary catastrophe. Our long-term future remains local, vulnerable, and dependent on one sun. If we can cross them, everything changes, not in a metaphorical way, but in an operational one. Resources become effectively unlimited on human timescales, because asteroids and moons become accessible inventories. Knowledge expands from one planetary laboratory to many, and experiments become distributed across environments. The story of life becomes a story of migration, not just survival, but nature sets prices, and the prices may be beyond what we can pay with today's tools. The question is not whether we can imagine the destination, because imagination is cheap. The question is whether we can afford the physics, because physics collects its debt. When we watch a montage of triumphs, we should also ask what the montage hides. So the question becomes precise, not poetic, and precision is where awe becomes real. What limits of physics, energy, propulsion, biology, and engineering make Pluto slow and Proxima unreachable within a lifetime? What technologies could bend those limits and which ones are fantasies in disguise? What would it take to turn a flyby age into an interstellar age? Pluto sits on our classroom maps like a final label, distant but still familiar, a neat dot at the edge of a tidy diagram. In practice, it is the first destination that punishes casual assumptions about travel, because the solar system is not drawn to scale, and time is not optional. The answer starts with a mission that succeeded by refusing to do the hardest part. New Horizons reached Pluto by committing to a one-way geometry, a path designed for a single, fast encounter. It did not plan to stop, it did not plan to turn around, and it did not plan to arrive in the everyday sense. It planned to pass through. On screen, that decision can look like a minor detail, but it is the central engineering choice. A flyby is an agreement with physics. You accept speed, and you accept that the world will rush past you. A rendezvous is a negotiation you must pay for, and the bill is written in velocity. New Horizons launched in January 2006 on an Atlas V, with a Star 48 upper stage, rising through the atmosphere like a bright pinprick against morning sky. The departure was among the fastest ever achieved from Earth, a deliberate attempt to buy time with raw launch energy. Fast in this context still meant years of coasting through darkness, because even record-setting speed is small compared to interplanetary distance. The early visuals of launch are all flame and vibration. Then, almost immediately, the story becomes quiet. The rocket is gone, the sky is empty, and the spacecraft is a cold, spinning machine shrinking into the black. That contrast is part of the lesson. Most deep space travel is not motion you can feel, but motion you must trust. Within months, the spacecraft crossed the orbit of Mars, cutting through the inner solar system where sunlight is still strong and radio contact feels routine. Then it headed outward toward Jupiter for a gravity assist, aiming for a moving target that would not wait. In early 2007, it flew past Jupiter and stole a small piece of the planet's orbital momentum, a theft permitted by celestial mechanics. That single encounter shortened the trip by years and raised the cruise speed. A gravity assist is sometimes described as a slingshot, but the metaphor hides the precision. The spacecraft does not bounce off a planet like a ball off a wall, because space has no fixed wall. Instead, it falls into the planet's gravity well and climbs back out, leaving in a new direction and at a new speed relative to the Sun. The gravity assist was not a trick that replaced propulsion, and it was not free energy in any magical sense. It was a trade that only works when the solar system's geometry cooperates, and when your approach is accurate to a narrow corridor. It required precise timing, careful targeting, and a target that was already moving at tens of kilometers per second. If you could freeze time and watch the encounter from above the solar system's plane, you would see a delicate curve. Jupiter's gravity bends the trajectory like a hand guiding a thread through a needle's eye, and the spacecraft departs with a slightly different share of the solar system's momentum. The planet barely notices, but the spacecraft's entire decade-long schedule changes. After Jupiter, the mission entered the long middle, the part that rarely makes headlines. For most of the flight, nothing dramatic happened, because deep space is mostly waiting, punctuated by checkouts, calibrations, and small corrections. Navigation became a slow conversation between star trackers, radio ranging, and careful thruster burns that were measured in meters per second. Those corrections matter because the target is not a bullseye painted on a wall. Pluto is moving, Earth is moving, and the spacecraft is moving, all while the Sun's gravity shapes every path. Over billions of kilometers, a tiny pointing error can grow into a miss measured in planetary diameters. In July 2015, nearly a decade after launch, New Horizons reached Pluto, and the arrival was really a crossing of an invisible gate. The encounter window was short because the spacecraft was moving too fast to linger, and because every instrument had a limited time to look. At closest approach, it covered thousands of kilometers each second, turning Pluto from a destination into a rapidly changing panorama. Visually, the moment is strange and beautiful. Pluto grows from a pale star into a disk, then into a world with a heart-shaped plain, blue haze, and dark, ancient terrain. Yet the spacecraft never slows to admire it, and the surface slides beneath the cameras like scenery seen from an express train. That speed is the first lesson, and it is a lesson in what you did not have to do. A flyby can be fast because it does not ask the spacecraft to match Pluto's motion around the Sun. It only asks for a precise crossing at a precise time, with the instruments ready and the antennas pointed when needed. A rendezvous is different, and the difference is not philosophical. To arrive and stay, you must cancel the relative velocity you carried in, which is called excess speed. You must pay for braking, and braking is not free just because you are already there, because the fuel must be launched and carried across the entire journey. This is the difference between getting there and staying there, and it is the difference between a photograph and a presence. Getting there can be a ballistic arc plus patience, shaped by gravity and small corrections. Staying there requires energy you must bring, or energy you must harvest, and the outer solar system offers little to harvest. New Horizons chose the flyby because the alternative was a mass problem that would cascade through the entire design. To break into orbit at Pluto, the spacecraft would need a large additional delta-v budget, measured in kilometers per second. That delta-v would demand propellant, and propellant would demand a larger launch vehicle, and the launch vehicle would demand higher cost and tighter constraints. Delta-v is the currency of space travel because missions are built from controlled changes in velocity, not from miles travelled. Every major event is a delta-v decision, whether it is dramatic or subtle. Leaving Earth, shaping the cruise, correcting the aim, and braking at the destination are all transactions in that same currency. The public often hears distance described in kilometers as if kilometers were the main obstacle. Engineers hear distance as time and delta-v because those drive power, mass, and risk, and because they determine what hardware must survive. A destination can be far yet easy to fly past, or closer yet hard to stop at. A spacecraft that wants to orbit Pluto must arrive with the ability to slow down by kilometers per second, and that requirement dominates the architecture. Chemical propulsion can provide that change, but only if you carry the propellant from the start sealed in tanks that must remain stable for years. Carrying it from the start makes the spacecraft heavier, which makes launch harder, which demands more propellant again. This compounding is the first glimpse of the rocket equation's logic, even before we write it down. More capability adds mass, and mass is stubborn. More mass demands more fuel, and more fuel adds mass again, and the loop grows quickly until the payload becomes the smallest part of the stack. In the inner solar system, you can sometimes compensate with sunlight, frequent communication, and shorter timelines. At Pluto, the same choices become brittle. Every kilogram you add to chase braking is a kilogram you cannot spend on instruments, shielding, redundancy, or antenna size. New Horizons was built around the decision to avoid that loop, and the spacecraft's silhouette reflects it. It carried a modest hydrazine system for small course corrections and attitude control, the kind of propellant used for careful nudges. It did not carry the propellant needed to erase its arrival speed at Pluto, because doing so would have rewritten the entire mission. That choice shaped everything else, including how the science had to be performed. Instruments were designed for rapid scanning rather than repeated passes, because there would be no second chance from a different angle. Observation sequences were rehearsed like choreography, because the spacecraft would not get a second orbit to fix mistakes. During the encounter, the spacecraft had to point cameras, spectrometers, and antennas in a planned sequence, often without waiting for instructions. The timing was unforgiving, because the geometry changed minute by minute as Pluto and its moons swept past. In deep space, later can mean never, and the mission design knows it. The flyby also shaped the data story, and it shaped what the public experienced. New Horizons could collect far more data than it could transmit quickly, because Pluto was too far for high data rates with the available power and antenna size. The spacecraft was like a field scientist with a notebook full of discoveries, trying to read them aloud across a canyon. So the spacecraft stored the encounter in memory and played it back slowly, like a recorder sending a message one careful syllable at a time. The most famous images were not a live broadcast, even though they felt like one. They were a delayed delivery, parceled out over months, and each new frame was a reminder of the distance. Pluto's distance makes communication a physical constraint, not a scheduling inconvenience. Radio signals weaken as they spread, and the spacecraft's transmitter power is limited by its energy source and thermal budget. The Deep Space Network can hear the whisper, but it cannot make the whisper louder, and it cannot shorten the time it takes to arrive. The light time delay to Pluto is measured in hours, depending on where Earth and Pluto are in their orbits. That delay changes operations because every command is a message into the past, and every response is a report from a spacecraft that has already moved on. Troubleshooting becomes slow, and autonomy becomes more valuable, because waiting for Earth can be fatal to a time-critical sequence. Even the act of confirming health becomes a kind of patience training. A signal leaves Earth, travels outward through the heliosphere, and arrives at a machine that has been alone for years. Then the reply begins its own long journey back, and the people who built the spacecraft must wait in silence. Pluto is also dynamically difficult in ways that stack together, and none of them are dramatic in isolation. It is far from the Sun, so sunlight is weak and solar panels are impractical at the scales we can launch. A Pluto orbiter must usually rely on nuclear power, which is scarce, regulated and heavy, and which sets limits on everything from instruments to transmitters. That power reality is visible in the spacecraft's design language. Instead of wide solar wings, New Horizons carried a compact radioisotope power source, turning heat from radioactive decay into electricity. The system is reliable, but it is not abundant, and every watt has to be budgeted like water in a desert. Low sunlight also affects thermal design and sensing, because the environment is both cold and dim. Temperatures are extremely low, and heaters must run to keep instruments within limits, even when power is precious. Heat is not a byproduct you can count on, because you cannot waste electricity generating it, and the spacecraft must balance warmth against longevity. Pluto's environment is not empty, but it is thin and challenging, and that thinness changes what is possible. Its atmosphere is tenuous and variable, a fragile envelope that can expand and contract with seasons over long timescales. Its gravity is weak, which means low orbital speeds, but it also means small margins for stable long-term operations near the surface. Weak gravity sounds like an advantage until you think about control. In a low-gravity system, small disturbances matter more, and orbital periods can be long and delicate. The spacecraft must navigate a region where tiny errors can accumulate, and where the gravitational influence of moons can complicate what would be simple elsewhere. Then there is the problem of gravity assists, which is really the problem of available leverage. The inner solar system offers many opportunities to borrow momentum, because planets are close together and move fast in tight orbits. The outer solar system offers fewer useful alignments, and the travel times between assists are long, which makes each attempt expensive in time. New Horizons use Jupiter because Jupiter is massive and reachable, a rare combination of power and accessibility. After Jupiter, there was no comparable stepping stone that helped with Pluto arrival, at least not within a reasonable schedule. The mission had already spent its best leverage early, and the rest of the trip was a long, efficient drift. A Pluto orbiter would face a harsher accounting, and the numbers would drive the narrative. It would need a trajectory that arrives with less excess speed, which usually means a longer flight and fewer opportunities to correct mistakes. Or it would need a powerful braking system, which usually means more mass and cost and a more demanding launch. Aerobraking is a common trick at planets with thick atmospheres, and it can save enormous propellant by letting air do the braking. Pluto cannot offer that in a reliable way because its atmosphere is too thin to provide consistent drag at safe altitudes. Even if it could, the thermal and navigation risks would be severe, because a small density change could mean a large trajectory change. So braking at Pluto usually means propulsion, and propulsion means propellant. Propellant means launch mass, and launch mass means a bigger rocket or a smaller payload, and those are the trade-offs that shape what science you can afford. The outer solar system does not forgive excess, because every extra kilogram echoes backward to the launch pad. This is why Pluto is not simply far, and why the phrase edge of the solar system can be misleading. It is far in a way that forces design compromises, because the outer solar system is a low-power, high-latency, low-resupply region. Every subsystem must be built to survive long periods without intervention, and to keep working when help is hours away. The timeline itself becomes a design parameter, not just a schedule on a calendar. A decade-long cruise demands components that do not drift out of calibration, and it demands mechanisms that do not seize after years of cold cycling. It demands software that remains reliable across years of radiation exposure and aging hardware, because you cannot reboot your way out of every failure. It also demands institutional endurance, which is an invisible part of the engineering. Teams change, budgets change, and priorities change, and the spacecraft keeps going anyway. A mission that lasts 10 years must survive more than engineering, because it must survive politics and patience, and it must keep its story coherent across generations of staff. New Horizons succeeded because it accepted those realities and narrowed its ambition without narrowing its curiosity. It aimed for a single, high-value encounter, then designed every system around that moment. It treated Pluto as a fleeting laboratory rather than a place to live, and in doing so it made the impossible achievable. That framing is the second lesson, and it is a lesson with a history behind it. Our greatest deep space successes often come from choosing flybys, not settlements, because flybys are how we buy science without paying the full cost of arrival. The early era of planetary exploration was built on this logic, and New Horizons is one of its most refined expressions. But flybys also reveal what we're not yet able to do, and they do it without judgment. They show us that we can touch the outer solar system, but we cannot easily stay there, at least not with the tools we routinely use. They show us that reaching is not the same as operating, and that a brief visit does not equal sustained presence. A long-term Pluto mission would need continuous power for years in deep cold, and it would need thermal stability through long seasons of darkness and dim light. It would need high reliability, because repairs are impossible and redundancy is expensive in mass. It would need higher data return, which means more power, a larger antenna, or new communication methods that can carry more bits across the same distance. It would also need a navigation strategy for a world with limited landmarks and long delays, where even small uncertainties can matter. At Pluto, you cannot joystick a spacecraft into orbit in real time, because the signal takes hours to arrive. You must trust pre-planned sequences and onboard fault protection, and you must accept that decisions will be made by software far from Earth. All of this sits inside the central question of the documentary, and Pluto is our first honest test. What limits of physics, energy, propulsion, biology, and engineering make some destinations effectively unreachable on human timelines? Pluto is our nearby test case, because it is still inside the Sun's domain, still bound to the same star that warms our oceans. Pluto also sets a tension point that the rest of the series will exploit, because it forces us to confront scale without abstraction. If a one-shot flyby took nearly a decade with a record-fast departure, what does that imply for anything beyond the planets? If stopping at Pluto is already a mass and energy crisis, what does stopping at another star require? The comparison is not rhetorical, and it is not meant as science fiction. Proxima Centauri is 4.24 light-years away, and a light-year is not a bigger kilometre. It is a unit that bakes time into the distance, because even light needs years, and nothing we build today approaches light speed. Pluto is measured in light hours, which already feels slow when you are waiting for a signal. Proxima is measured in light years, which is slow in a way that changes the meaning of the word mission. The gap between those units is the gap between difficult and alien, between engineering problems and civilization-level commitments. New Horizons shows the best version of chemical era reach, and it does so with clarity. It used Earth's launch energy, then borrowed from Jupiter, then coasted efficiently through the outer darkness. It arrived with enough precision to thread a narrow window at high speed and to turn a distant dot into a mapped world. It also arrived with no practical way to break into orbit, because the mission could not afford that delta V. That is not a failure of courage or planning, and it is not a lack of imagination. It is the price tag of physics expressed in mass, and mass is the one thing you must lift off Earth before anything else can happen. So Pluto becomes a mirror, and it is a mirror that reflects our limits without exaggeration. It reflects the constraints that are easy to ignore when we talk about exploration in headlines. Because headlines compress time the way maps compress space, it forces us to say the quiet part out loud. That speed is expensive, and stopping is even more expensive. And it invites an uncomfortable thought experiment. If you had the perfect map, the perfect camera, and the perfect will, would that change the delta V you must pay? Or would it only make the bill more visible? Pluto taught us that distance is not the only bill, even though distance is what our maps emphasize. The deeper bill is velocity, because every mission is built from paid changes in speed, carefully scheduled, brutally finite, and indifferent to our wishes. Engineers call that change delta V, and it behaves like a budget that never forgives overspending. You can coast for years in silence, watching stars drift across a black window, but you cannot coast into orbit. If you arrive with the wrong speed, you arrive with the wrong future. To leave Earth at all, you must climb out of a gravity well, and that climb costs delta V. Gravity is not a wall you break through, but a debt you keep paying while you rise. To then reshape your solar orbit, you must pay again, because the sun keeps the books. This is where the public intuition breaks, because getting free of Earth feels like the hard part. In practice, escaping Earth is only the down payment on the trip, and the interest is charged by orbital mechanics. From orbit, you're not done with gravity. You're simply negotiating with a larger landlord. A rocket is not like a car that carries fuel as a minor detail. A rocket carries its fuel as most of its mass, and that fact dominates everything you can do later. On the launch pad, the vehicle looks tall and purposeful, yet most of it is propellant waiting to become exhaust. The core rule is simple to say and brutal to live with. To go faster, you must throw mass backward faster, and you must carry that mass from the start. Newton's third law is the quiet signature on every launch contract: action and reaction, paid in kilograms. The Tsiolkovsky rocket equation formalizes this trap, but the idea can be understood without algebra. Your final speed change depends on exhaust velocity and on how much of your starting mass is propellant. Once you accept that, the rest is accounting. Exhaust velocity is the speed of the propellant leaving the engine. Higher exhaust velocity means each kilogram of propellant buys more delta V because it carries more momentum away. In plain terms, you get more kick per kilogram when the exhaust leaves faster. The other lever is mass ratio, which is the full rocket divided by the empty rocket. A larger mass ratio means you start heavy with propellant and end light, and that difference is what you spend. When the tanks run dry, the remaining structure becomes the bill you still have to carry. The equation ties these levers together with a logarithm, which is nature's way of saying diminishing returns. Each extra bit of delta V demands a larger and larger fraction of your launch mass, and the curve steepens exactly when ambition rises. The math is compact, but the consequences are enormous. The conceptual loop is the tyranny hidden inside every launch. More delta V requires more propellant, but propellant has mass, so you need more propellant to push the propellant. The rocket is forced to lift its own future decisions. That loop is not linear, and it is not polite. It grows toward an exponential wall where payload becomes a rounding error and tanks become the mission. At the extreme, you are no longer designing a spacecraft, you are designing a propellant delivery system. This is why just add more fuel fails as a strategy. Adding fuel increases the mass you must accelerate, so the added fuel partly pays for itself and partly pays for the privilege of existing. The rocket equation turns common sense into a trap because fuel is both solution and problem. At some point, most of your fuel is not buying speed for the payload. It is buying speed for other fuel that you also had to lift, and that recursion is where missions become impossible. The payload sits at the top like a crown, while the stack beneath it is mostly sacrifice. Even the structure that holds propellant becomes a penalty. Bigger tanks need stronger walls add mass, and that mass demands more propellant again. Engineers fight this with lightweight alloys, composites, and clever geometries, yet physics still collects its fee. Earth makes the problem worse, because you must lift everything through gravity and atmosphere. The rocket equation does not care that you start on a planet, but your vehicle does, because thrust must exceed weight. In the lower atmosphere, drag and gravity losses quietly steal delta V you never meant to spend. For a typical chemical launch, the stack on the pad is mostly propellant, with a thin sliver of payload. The spectacle of launch is the sound of mass ratio, thunder, shock diamonds, and a bright plume carving air into turbulence. As the vehicle climbs, it becomes lighter by the second, and only then does it begin to feel powerful. Once you reach orbit, the accounting does not stop. Orbit is not halfway to anywhere. It is merely a stable place to begin paying for interplanetary speed. The planet below is still pulling, and the sun is already shaping your next arc. A spacecraft bound for Pluto needs a heliocentric trajectory that reaches Pluto's distance at the right time. That requires changing your solar orbit, not just leaving Earth, because you must meet Pluto where it will be. In spaceflight, arriving is not about distance, it is about timing and velocity. The delta V to escape Earth is significant, but the delta V to reshape your path around the sun often dominates mission design. The sun is the main gravity well, and Earth is only a local complication. When you leave Earth, you do not leave gravity, you switch which gravity matters most. New Horizons illustrates the logic by what it did not do. It paid for a fast departure, then used Jupiter to borrow additional speed without carrying extra propellant. In the visuals, Jupiter is not just a planet, it is a moving reservoir of momentum. Gravity assists are not a loophole in the rocket equation, but they are a way to change velocity without expending onboard reaction mass. They trade time and geometry for delta V, and they demand precision measured in kilometers across billions of kilometers. The spacecraft threads a needle, and the reward is speed. They also reveal the scarcity of options because assists require alignments that do not happen on demand. A planet must be where you need it, moving how you need it, and the window can be narrow. Miss it, and the next opportunity may be years away. When assists are unavailable, you must bring the delta V yourself. That is when the rocket equation becomes the mission's dominant character, shaping everything from mass to schedule. The trajectory stops being a choice and becomes a consequence. To see why chemical rockets scale poorly, we need to compare propulsion by exhaust velocity, often expressed as specific impulse. Specific impulse is efficiency in disguise, measured as seconds of thrust per unit weight flow. Higher specific impulse means you get more impulse from the same propellant weight. Chemical engines have high thrust and modest specific impulse. They can lift off Earth and make big burns quickly, but their exhaust velocity is limited by chemical energy. In a launch sequence, that high thrust is everything. Without it, you never reach the clean simplicity of vacuum. The limit is not engineering laziness, it is chemistry. Chemical bonds release energy on the scale of electron volts, while high exhaust velocity demands far more energy per kilogram. Even perfect combustion cannot change what molecules are willing to give, so chemical rockets are excellent for short, forceful pushes. They are poor at accumulating extreme delta V without becoming mostly propellant, because the exhaust velocity ceiling forces mass ratio to do the work. The result is a vehicle that grows faster than its capability. Ion propulsion flips the trade. Ion engines can reach very high exhaust velocities, which means high specific impulse and far better propellant efficiency. In imagery, the plume is often invisible, just a faint bluish whisper in the dark. But ion engines produce low thrust because they accelerate small amounts of propellant with limited power. They are marathon engines, not sprinters, and their strength is patience. The spacecraft does not leap forward. It steadily rewrites its orbit one day at a time. Low thrust changes mission shape. You cannot punch out of Earth's gravity well with ions alone, because you would spend too long fighting gravity losses. While you push gently, gravity pulls continuously, and much of your effort cancels itself. In deep space, low thrust can be a gift because you can keep pushing for months. Over long durations, that steady push can accumulate large delta V, and it can do so with very little propellant. The trade is that navigation becomes a slow sculpture, not a single decisive stroke. Yet ion propulsion is not a magic wand for Pluto or Proxima, because power becomes the constraint. To get more thrust, you need more electrical power, and power systems add mass. The rocket equation returns through the side door disguised as radiators, cables, and structure. Solar power also fades with distance, dropping with the square of your distance from the sun. At Pluto, sunlight is so weak that huge arrays become impractical, and they would be fragile in the cold. The sun is still bright to our eyes, but out there it is a small, hard star. Nuclear electric power can help, but it is heavy and politically constrained, and it creates waste heat that must be rejected. High power in space is never just a box you bolt on, because heat must go somewhere. In vacuum, the only way out is radiation, and radiators are mass. Nuclear thermal rockets sit between chemical and ion in performance. They heat hydrogen with a reactor and expel it through a nozzle, achieving higher exhaust velocity than chemical engines. Historically, this idea has been tested on Earth, where the promise was real and the complications were immediate. Nuclear thermal offers high thrust with better specific impulse than chemical, which makes it attractive for fast transfers. It also brings complexity, safety concerns, and a reactor that must survive launch. Even if the physics works, the program must survive politics, budgets, and public fear. Even nuclear thermal does not erase the rocket equation. Higher exhaust velocity helps, but the mass ratio problem remains when delta V targets become extreme. You can bend the curve, but you cannot flatten it into kindness. For Pluto, nuclear thermal could shorten travel times, but it does not make breaking into orbit cheap. For Proxima, it is still orders of magnitude short of what is needed, because interstellar speeds are a different regime. The numbers stop being merely large and start being alien. The deeper lesson is that propulsion types trade three currencies. They trade thrust, exhaust velocity, and power, and you rarely get all three at once. When one improves, another usually becomes the bottleneck. High thrust helps you leave planets and perform quick maneuvers. High exhaust velocity helps you avoid hauling mountains of propellant. High power helps you run high exhaust velocity at meaningful thrust, but power systems are heavy and thermally demanding. Every choice moves the burden, it does not delete it. You can shift mass into propellant, or into structure, or into power and heat rejection, yet the mission still carries the total. The rocket equation is not a design preference, it is a conservation law made practical. The rocket equation also explains why fast missions often avoid stopping. A flyby can accept high arrival speed, while an orbiter must pay to match the target. In the visuals, a flyby is a bright streak past a world, while orbit is a careful spiral into companionship. To orbit Pluto, you must cancel your excess velocity relative to Pluto. That braking delta V must be carried from the beginning, which means you pay for it at launch. The fuel you need near Pluto is fuel you must accelerate away from Earth. This is the part that feels backward to intuition. The fuel you need at the end is the fuel you must accelerate for the entire trip, and that makes late decisions early burdens. A mission's final act is written into its opening mass, so the cost of braking is multiplied by the cost of carrying the braking fuel. The rocket equation makes late requirements become early mass, and early mass becomes late limitations. This is why designers fear requirements creep, because it grows like compound interest. The same logic applies to returning home. A round trip is not two one-way trips, because each leg's propellant must be carried through the other leg's burns. The vehicle becomes a stack of future obligations, and the stack must survive every burn. This compounding is why deep space architecture becomes obsessed with staging. Staging is the act of throwing away empty tanks and engines to reduce dead mass, and it is as old as rocketry itself. The moment a tank is empty, it becomes a liability you should stop accelerating. Staging works because the rocket equation punishes carrying empty structure. If you can discard that structure, your remaining propellant pushes a lighter vehicle, and the same engine suddenly feels stronger. In footage, staging is dramatic. An abrupt separation, a flash, and a falling shell. Every stage is a reset of the mass ratio problem. You start heavy, burn propellant, then drop the empty shell and start heavy again with a smaller vehicle. The vehicle sheds weight like a climber dropping gear to reach the summit. Staging is not optional for chemical rockets leaving Earth. Without staging, the required mass ratio would demand impossible tank fractions and impossible structural strength. The history of launch vehicles is, in part, a history of learning how to separate reliably. But staging has limits and costs. Each stage adds engines, plumbing, separation systems, guidance complexity, and more failure points. The design becomes a choreography of events that must happen in the right order, at the right millisecond. Stages also impose manufacturing and testing burdens, because each stage must work perfectly in sequence. Reliability becomes a probability chain, and chains break at weak links. A single stuck valve can erase years of planning. Staging helps most when you can drop stages early, near Earth, where gravity and atmosphere make dead mass especially expensive. In deep space, staging is harder to justify, because you're throwing away hardware you might wish you had later. The farther you go, the less you can afford surprises. A deep space stage must coast for years, then restart reliably after cold soaking and radiation exposure. That requirement adds mass and reduces the benefit, because insulation, heaters, and redundancy are not free. Space is gentle in force but harsh in time. There are also operational limits. If you stage too aggressively, you create debris and tracking challenges, and you complicate mission timelines and risk assessments. Mission control must know what is where, even when where is a widening cloud of orbits. Even with staging, chemical rockets hit a wall when delta-V goals rise. The payload fraction shrinks until the mission becomes mostly propellant logistics, and the science instruments become passengers. The tyranny is not that we cannot build rockets, but that rockets must obey arithmetic. This is why mission designers chase every alternative source of delta-V. They use gravity assists, they use aerobraking where atmospheres allow it, and they accept flybys. Each technique is a way of letting nature do part of the work. Aerobraking is powerful because it uses a planet's atmosphere as reaction mass. It can replace large propellant burns with controlled friction and heat management, turning air into a brake pad. In visuals, the spacecraft skims the upper haze, glowing faintly as energy becomes heat. Yet aerobraking is only available at worlds with thick, predictable atmospheres. Pluto cannot offer it reliably, and Proxima offers no atmosphere until you arrive. Even when air exists, it can be variable, dusty, or chemically hostile. So the rocket equation keeps returning, like a refrain. If you cannot borrow delta V from planets or air, you must buy it with propellant and exhaust velocity. The universe does not forbid travel, it simply invoices it. At this point, the narrative shifts from mechanics to meaning. Delta V is not just a technical number, it is the boundary between visiting and operating. It separates a brief encounter from a sustained relationship. A spacecraft that can change speed freely can rendezvous, orbit, and redirect to new targets. A spacecraft with limited delta V is locked into a narrow script, and the script must be written years in advance. How much exploration is possible when improvisation is unaffordable? Pluto missions reveal that script clearly. The fastest practical missions are flybys, because the delta V to stop is more than the mission can afford. The reward is a rush of data, a burst of images, and then the world falls behind forever. Interstellar missions amplify the same logic until it becomes almost absurd. To reach Proxima within a human lifetime, you need a delta V that is a significant fraction of light speed. At that scale, even dust becomes a hazard, and speed becomes its own environment. At those speeds, the rocket equation becomes catastrophic for any rocket that carries its reaction mass. Even with very high exhaust velocity, the required mass ratios become unbuildable. The vehicle would need to be mostly propellant, then mostly propellant to push that propellant, and so on. This is where people propose perfect rockets, and the chapter must address the temptation. Suppose you had flawless engines and perfect tanks, with no structural penalties, no leaks, and no margins. Even then, the rocket equation still demands propellant, and propellant still demands mass ratio. Perfection improves margins, but it does not change the exponential shape. The curve may shift, but it does not stop curving, and the wall does not move far enough. The tyranny is not sloppy engineering, it is the mathematics of momentum. So the question becomes, what could change the shape? The only escape is to stop carrying all your reaction mass, or to use an energy source far beyond chemistry. That is why so many proposals feel like they belong to science fiction, even when the physics is real. Beamed sails, external propulsion, and in situ propellant harvesting are attempts to move the burden off the vehicle. They are not easy, but they attack the right constraint because they change what the spacecraft must carry. The dream is to travel light and let the infrastructure do the heavy lifting. For now, within conventional rockets, the tyranny remains. Every kilogram of payload is negotiated against kilograms of propellant and kilograms of structure, and the negotiation is unforgiving. The launch vehicle is a balance sheet rendered in metal. That negotiation is why escaping Earth is only the first bill. The bigger bill is the sequence of speed changes after you are free, because interplanetary travel is orbit change. You must match planes, match timing, and match velocities, all while the planets keep moving. The mission is not a straight line, it is a choreography of momentum. In animation, the orbits look like nested rings, yet the transfer path is a slanted thread, an elegant curve that exists only if you pay for it. The spacecraft is not aiming at where Pluto is, but where Pluto will be. The rocket equation turns that choreography into a mass problem. It forces you to decide what you can afford to do, not what you would like to do. It also forces humility because the solar system is spacious, but it is not generous. This is the hidden reason our exploration feels both triumphant and constrained. We can reach many places, but we often cannot arrive gently, stay long, or come back. The images are breathtaking, yet the trajectories are often one-way commitments. The chapter's final turn is toward the next barrier, because propulsion is only half the story. Even if you could build the perfect rocket, speed is stored energy, and stored energy must be managed. The faster you go, the more your spacecraft becomes an energy system with a payload attached. Kinetic energy grows with the square of velocity, so ambition becomes expensive faster than intuition expects. Doubling speed demands 4 times the energy, and that energy must come from somewhere. When you picture a faster mission, you're also picturing a much larger power bill. Energy must be generated, stored, and converted into exhaust momentum, and every step produces waste heat. The faster you want to go, the more your spacecraft becomes a power plant, and the more it must radiate heat into darkness. In space, heat is slow to leave, and that slowness becomes design. So the rocket equation is the first tyranny, written in mass and exponential scaling. The next tyranny is energy, written in squares and in heat you must survive. In the next chapter, we follow that energy bill to its source, and we ask what fast costs in joules and infrastructure. Chapter 3 ended with a hard pivot, and it deserves to linger on screen for a moment. Mass is tyranny, but speed is stored energy. To ask for a faster Pluto mission is to ask for more energy on departure, delivered in a shorter and harsher burst. To ask for Proxima within a lifetime is to ask for energy on a civilizational scale, generated, controlled, and aimed with precision. Distance feels like the obstacle because distance is what maps show, and maps are honest about emptiness. Physics treats distance as time multiplied by velocity, and velocity is paid for in joules, whether we like the price or not. So the chapter opens with a deceptively simple invoice: kinetic energy. It is the cleanest bill for speed, and it scales with mass and with velocity squared, which is where human intuition quietly breaks. At low speeds, the curve looks gentle and negotiable, like a hill you can climb by trying harder. As speed rises, the curve steepens into something more like a wall, until every extra day saved costs a shocking amount. The rule is compact and brutal, and it does not bargain. Double the speed and you need 4 times the kinetic energy. That means cutting travel time in half is not a modest upgrade, and it is not a clever optimization. It is a demand for roughly 4 times the energy, before you count inefficiencies, margins, and the ugly realities of hardware. Put the equation away and keep the feeling. A car at twice the speed does not just feel riskier, it carries far more crash energy, and that energy has to go somewhere when things go wrong. You can visualize it in slow motion: metal folding, glass bursting, heat blooming at the point of impact. The violence is not just drama, it is physics converting stored motion into deformation and heat. Another analogy is climbing, because it separates 2 kinds of effort we often confuse. Doubling the height doubles the work, but doubling speed squares the energy stored in motion, and that difference matters. This is why a little faster is rarely little in deep space, even when the numbers look modest. The mission stops being a trajectory problem and becomes an energy production problem, which is a different kind of constraint. For Pluto, the baseline is already severe, and the history is instructive. New Horizons bought speed with a powerful launch and a Jupiter assist, then accepted a flyby to avoid braking. In the visuals, the spacecraft is a bright speck leaving Earth, then a tighter shot of Jupiter's swirling clouds as it steals momentum. The assist is elegant, but it is also a confession. We could not afford to arrive and stop. If we demand a Pluto orbiter that arrives quickly, we demand both high departure energy and high arrival control, and those are separate bills. The energy bill grows on both ends, and the second end is the one people forget. Engineers often speak in delta V because it fits the rocket equation, and it fits the way missions are planned. Energy is the deeper accounting, the one that explains why large delta V becomes punishing when speed is already high. Delta V adds linearly, which can sound manageable, like stacking small upgrades. Energy does not behave that way, because the same extra kilometers per second cost more when you're already moving fast. That is the first reframing of this chapter, and it changes the emotional tone of planning. Fast enough is not a number on a speedometer, it is a budget line that curves upward. Now add the part that headlines skip because it complicates the triumph. Getting up to speed is only half the story if you want to stop. A flyby can spend all its energy on arrival speed and still succeed, because success is defined as passing close enough to measure. A rendezvous must erase that speed relative to the destination, and the word erase is doing heavy work. This is the 2 burns problem, and it is as old as spaceflight itself. You accelerate to build kinetic energy, then you must spend comparable energy again to remove it. Braking is not free in space, and the emptiness is the reason. With no air and no road, stopping means throwing momentum away using propellant, fields, or external infrastructure. On Earth, friction and atmosphere do the bookkeeping for us, quietly and constantly. In space, nothing reaches out to help, so you must bring your own mechanism for changing velocity. For Pluto, that second burn is the hidden wall, and it appears late in the planning. You arrive fast because you paid for speed, then you discover you cannot afford to cancel it. The symmetry is easy to state, and hard to accept when budgets and mass limits appear. If you want to arrive at the same speed you left, you must pay twice. In practice, it is worse than twice, and the reason is mechanical rather than philosophical. The fuel for braking must be carried during acceleration, so the rocket equation multiplies the demand. The visuals here are simple and cruel. A bar chart of propellant mass growing, then growing again, then swallowing the payload. Each added kilogram of fuel requires more fuel to push it, and the spiral tightens. This is why fast missions often choose not to arrive, even when the destination is scientifically irresistible. They choose to pass through, because stopping turns a sprint into a freight problem. A flyby is a camera shutter snapping at interplanetary speed, and the timing is unforgiving. The target world grows from a dot to a disk to a landscape in hours, then vanishes behind you forever. For interstellar travel, the two burns problem becomes existential, because the speeds under discussion are no longer a few tens of kilometers per second. A probe that accelerates to a significant fraction of light speed cannot casually brake near Proxima. If it does not brake, it is not an arrival in any human sense, even if the trajectory is perfect. It is a brief flash through a foreign system, with seconds or minutes to observe. Imagine the star field barely shifting for years, then suddenly blooming into a storm of light and geometry. Planets, if they exist, would streak past as unresolved crescents, and the encounter would be over before comprehension catches up. If it does break, the mission becomes a full energy cycle that must close cleanly. You must accelerate a payload and then decelerate it, and both legs demand immense energy. At this point, the narrative must widen beyond Newtonian intuition, because the old formulas stop telling the whole truth. At high fractions of light speed, relativity changes the bookkeeping. We do not need heavy math to feel the effect, and we do not need to memorize symbols. As you approach light speed, each additional increase in speed costs disproportionately more energy. The spacecraft's kinetic energy no longer follows the simple low-speed formula, because momentum and energy behave differently near the limit. The required energy climbs faster, and the practical ceiling tightens. Relativity also changes engineering constraints in ways that feel almost unfair. Time dilation can help the travelers, but it does not help the launch pad that must supply the energy. From the ship's perspective, the trip can shrink, and clocks can run slow. From Earth's perspective, the bill still arrives in full, and the power plant does not get a discount. The universe enforces a speed limit by pricing, and the metaphor is accurate. Light speed is not a wall you hit, it is a cost curve that goes vertical. Even before relativistic speeds, another constraint appears, and it is the one that breaks many optimistic schedules. Energy is the total bill, but power is how fast you must pay it. Energy is measured in joules, and it accumulates over time like water in a reservoir. Power is joules per second, and it determines whether you can accelerate quickly or only gradually. High-thrust engines are power-hungry, and the hunger is immediate. They must deliver enormous energy in short bursts to push hard against inertia. Low-thrust engines can be energy efficient, but they are power-limited, and the limitation is practical. They sip energy over months or years, and they demand patience from everyone watching. This is a key distinction for fast enough, because it separates what is possible in principle from what is possible on a deadline. A mission can have enough total energy in theory, yet lack the power to apply it on schedule. Chemical rockets are the classic high-power approach, and their history is visible in archival footage. They release energy quickly, producing high thrust, but they carry limited energy per kilogram. The exhaust plume is not just fire, it is mass thrown backward at high speed. The chemistry is a compact battery, but it is a battery you must lift along with everything else. That is why chemical propulsion is good at leaving Earth, where gravity demands a strong shove. It is poor at reaching extreme speeds once you're already deep in space and chasing more velocity. Electric propulsion is the opposite, and its visuals are almost quiet. It can achieve high exhaust velocity, but thrust is capped by available electrical power. A faint blue ion glow looks gentle, yet it can run for thousands of hours, steadily rewriting an orbit. The trade is clear: less push per second, more push per year. To make electric propulsion fast, you must raise power dramatically, and power brings consequences. That means larger reactors or arrays, larger radiators, and more mass devoted to heat. Heat is the quiet tax on power, and it is relentless in vacuum. Every conversion step wastes energy, and in space waste, heat must be radiated away slowly. As power rises, radiator area rises, and the geometry starts to dominate the design. The spacecraft becomes less like a vehicle, and more like a thermal management system with a payload. You can picture wide, dark panels unfolding like wings, not for lift, but for survival. They glow in infrared, bleeding away the byproduct of doing work. This is where the energy framing connects back to Chapter 3, and the connection is not abstract. The rocket equation punishes mass, and high-power systems add mass aggressively. A fast ship needs both high energy and high power, and it needs them in the right places. High energy demands a potent source, and high power demands hardware that survives heat and stress. Now return to Pluto with this lens, because Pluto is where these ideas become concrete rather than speculative. To cut a decade to a few years, you do not just need a better trajectory, you need a much larger energy injection near Earth, or sustained power over the cruise, or both, and each option forces a larger launch mass. That mass then asks for more energy again, tightening the loop. A gravity assist can shift velocity without onboard propellant, and it remains one of the most beautiful tricks in astrodynamics. But it cannot create arbitrary speed because it is bounded by planetary motion and alignment windows. The planet is not a free engine, it is a moving partner, and the choreography must be available when you need it. Miss the window, and the same trick can require years of waiting. So energy still rules the schedule, even when gravity helps with the accounting. You can borrow some momentum from planets, but you cannot borrow your way to interstellar fractions of c. For Proxima, the energy numbers become the story, and they become the dominant character in the script. Even a small fraction of light speed implies kinetic energy comparable to large national energy budgets. The exact figures vary with payload mass and target speed, and the assumptions matter. The qualitative truth is stable and alarming, because the v-squared term dominates quickly. This is why the central question keeps returning, even when the imagery is romantic. The limits are not only distance and courage, they are energy generation and delivery. If we imagine a 1-ton probe to Proxima, the energy to reach high speed is enormous, even before redundancy and shielding. If we imagine a crewed ship, it becomes almost unthinkable under familiar economics. Then add deceleration again, because arrival is not a postcard moment, it is a commitment. To arrive and stay, you must remove that kinetic energy, and you must do it without an atmosphere to brake against. In the solar system, planets with thick air can help, and aerobraking has a long pragmatic history. At Proxima, you cannot count on a convenient brake, and you cannot count on a prepared infrastructure. This is where many proposals pivot to externalization, because carrying everything on board is so punishing. If the ship does not carry all its energy, something else must supply it. Beamed propulsion is the cleanest example, and it fits the theme of paying from a distance. A distant laser or microwave array pushes a sail, moving the energy source off the spacecraft. That can reduce onboard mass, which helps the rocket equation in the most direct way. It also demands extreme power generation, extreme pointing accuracy, and immense optics. In visual terms, it is a cathedral of light, an array spanning kilometers, phase-locked and steady. The beam must stay on a target that becomes smaller than a pixel as it recedes. It introduces a new fragility, and the fragility is not subtle. The propulsion system is now a long-range link, and the mission depends on maintaining that link for years. It also does not solve braking by itself, which brings us back to the symmetry we keep trying to escape. A sail pushed from behind must still slow down, which implies a second beam, a second sail mode, or a new trick. Magnetic braking against the interstellar medium is sometimes proposed, and the concept is simple to say. The medium is thin, so the required structures become huge and difficult. A destination laser array could break an incoming sail, which sounds neat until you speak the implication aloud. That implies pre-built infrastructure at Proxima, which is a paradox for a first mission. So the two burns problem becomes a design filter, and it removes more concepts than it keeps. Many concepts can accelerate something, far fewer can accelerate and decelerate within a lifetime. Relativity sharpens that filter, and it does so without drama or malice. As speeds rise, the energy gap between fast and faster grows, and the engineering margins shrink. Even at lower fractions of c, the environment changes in ways that feel like a warning label. Dust impacts become energetic, radiation exposure rises, and shielding mass increases. A grain of dust at extreme speed is not a speck, it is a projectile with explosive energy. The ship's forward face becomes a sacrificial surface, and the design becomes about surviving a long, invisible hail. Shielding mass feeds back into energy demand, and the feedback is immediate. more mass requires more kinetic energy at the same speed, and the loop tightens. This chapter's goal is not to declare defeat, and it is not to romanticize impossibility. It is to name the real distance, which is energy, and to show why speed is expensive. Pluto and Proxima sit on the same curve, and that curve is the quiet protagonist of modern exploration. Pluto is the near end where we can still negotiate, and Proxima is where negotiation becomes infrastructure. Awe belongs here because the numbers are not just big, they are revealing. They show how much of the universe is locked behind energy thresholds, like doors that open only when the power is available. We have touched the moon and reached the planets because the energy steps were within reach of our tools and our politics. The next steps demand energy density, power and control we do not yet command. So fast enough becomes a question of what we can generate, store and reject as heat, without drowning the payload in support systems. It becomes a question of what we can afford to throw away as exhaust. And it becomes a question of honesty, because every schedule is a disguised energy plan. When we ask for shorter travel times, we are really asking where the extra joules will come from. This reframing sets up the next move in the series, and it points forward without promising miracles. If energy is the distance, then propulsion is the method of paying. The next chapter examines what propulsion can realistically do beyond chemical rockets, and it keeps the same accounting rules. It asks which ideas change the curve and which only rename the bill. Chapter 4. Reframed distance as energy, and energy as a bill that compounds with speed. Now we test the payment methods we actually know how to build, and we watch where the numbers stop being inspirational and start being structural. Propulsion is not one problem, it is several problems tied together by physics. You need momentum change, you need power delivery, you need heat rejection, and you need reliability that lasts years. You also need guidance and control that stays stable while thrust is applied, because even tiny misalignments can waste months of work. Every engine concept promises one miracle, and then reveals its invoice. The invoice is mass, or heat, or fuel, or containment, or infrastructure, or economics. Sometimes the invoice is time, because a propulsion system can be elegant and still arrive too late to matter. Start with what already works in deep space: electric propulsion. Ion and Hall thrusters trade thrust for efficiency, pushing tiny propellant flows to extreme exhaust velocities. In simple terms, they throw propellant out the back very fast, which makes each kilogram of propellant do more useful work. Ion engines typically use grids and high voltages to accelerate ions in a narrow beam. Hall thrusters use an electric field and a magnetic field to accelerate plasma in a wider plume. Either way, the exhaust velocity is far higher than chemical rockets, which means the specific impulse can be measured in thousands of seconds. That efficiency is real and mission-changing for probes. A small tank can support months of thrusting, and the accumulated delta V can be enormous. On screen, the thrust looks like almost nothing, just a faint bluish glow. Yet the spacecraft's trajectory slowly, relentlessly bends. Historically, this was not a theoretical victory but a practical one. Deep Space One demonstrated ion propulsion as a primary engine, and missions like Dawn used it to visit multiple bodies in the asteroid belt. These spacecraft did not sprint. They climbed out of gravity wells like mountaineers, patient and persistent, but the thrust is tiny, because thrust is limited by electrical power. If you want more push per second, you must supply more watts and carry the hardware. The physics is blunt. Power turns into kinetic energy of exhaust, and energy per second is exactly what power means. There is another limiter hiding inside the thruster itself. High exhaust velocity can erode grids, sputter materials, and slowly change performance, so lifetime becomes a design constraint. A probe can accept gradual degradation, but a crewed vehicle must treat it like a safety-critical system. For cargo, that trade can be perfect. A slow spiral outward is acceptable when the payload is instruments, propellant, or supplies that can arrive later. You can even imagine a logistics chain, uncrewed freighters departing years ahead, building a quiet reservoir of resources. For rapid human travel, tiny thrust becomes a schedule killer. People do not tolerate multi-year accelerations at fractions of a millimeter per second squared. Even if the crew could endure the calendar time, the mission would accumulate exposure to hazards that scale with duration. Electric propulsion also exposes the power problem that Chapter 4 warned about. Solar arrays fade with distance, because sunlight drops with the square of range. That is not a gentle decline, it is a cliff in slow motion, twice as far means 4 times less power. Near Earth, solar electric can be strong and scalable. Past Mars, arrays grow large, fragile and heavy, and pointing and degradation become constant concerns. Visually, the spacecraft starts to resemble a flying power plant, with wings that dominate the silhouette more than the payload does. Solar arrays also have their own aging mechanisms. Radiation darkens materials, micrometeoroids pit surfaces, and thermal cycling stresses joints and wiring. Each year in deep space is a long endurance test, and the power margin tends to shrink rather than grow. At Jupiter and beyond, solar still works for some missions, but the margins tighten. At Pluto, sunlight is so weak that arrays become an architectural burden. The camera can linger on a distant sun that looks less like a furnace and more like a bright star, because that is what it becomes. So electric propulsion pushes you toward nuclear power. Nuclear electric can run far from the sun, but reactors and shielding add mass and political complexity. The moment you say reactor, the mission becomes not only engineering, but also governance, licensing, and public trust. High-power electric also creates a thermal trap. In vacuum, you cannot dump heat into air, so radiators must glow it away, and radiators are structure. Heat has to leave as infrared light, which means surface area becomes a kind of currency that you must buy with mass. The result is a familiar loop. More power enables more thrust, but more power demands more mass and more radiator area, which demands more thrust again. The spacecraft begins to look like a compromise between an engine and a set of wings, except the wings are hot panels designed to shine waste heat into darkness. Electric propulsion is therefore a precision tool, not a universal solution. It excels when time is available and when power can be sustained for years. It is the quiet workhorse of robotic exploration, and it is a reminder that efficiency does not automatically mean speed. If electric is the marathon, nuclear thermal is the heavy shove. A nuclear thermal rocket heats hydrogen in a reactor and expands it through a nozzle. The hydrogen never burns in oxygen, it simply absorbs heat and becomes a furious high-speed exhaust. The performance sits between chemical and electric. You get higher exhaust velocity than chemical, and you keep thrust high enough for decisive burns. That matters because high thrust lets you depart planets quickly, execute mid-course corrections cleanly, and capture into orbit without endless spirals. This idea is not new, and that history carries weight. During the Cold War, the NERVA program tested nuclear thermal engines on the ground, and the results were technically impressive. The program ended not because the physics failed, but because budgets, priorities, and politics shifted. That combination is why nuclear thermal keeps returning in studies for faster Mars transfers. It could shorten trip times and reduce propellant mass for some missions. Shorter trips are not just convenient, they reduce exposure to radiation and reduce the psychological load of confinement. But nuclear thermal carries its own walls. The reactor must be compact, robust, and safe through launch accidents, which is an engineering and political gauntlet. The design must assume worst-case scenarios, including a launch failure that scatters hardware into ocean or land. Hydrogen is also difficult to store for long durations. It boils off, it leaks, and it demands insulation and active cooling that add mass and failure modes. In visuals, the tank becomes enormous, because hydrogen is light by mass but bulky by volume. Then, there is reliability across deep time. A crewed ship needs engines that restart after months, valves that do not seize, and fuel lines that do not embrittle. Hydrogen can permeate materials and cause cracking, so the plumbing is not a footnote, it is a mission risk. Even if nuclear thermal works perfectly, it does not erase the two burns problem. A fast Pluto mission still needs braking, and braking still multiplies propellant. The rocket equation does not care that the destination is beautiful, it only cares about delta V and mass ratio. That symmetry is easy to forget when we imagine a dramatic departure burn. Acceleration feels like progress, while deceleration feels like an afterthought, yet the math treats them as equals. If you want to arrive fast, you must spend nearly as much effort arriving safely. For Proxima, nuclear thermal is not even in the right category. It cannot reach interstellar fractions of C without impossible mass ratios and impossible fuel logistics. Even optimistic exhaust velocities remain far too low, so the propellant fraction explodes until the vehicle becomes mostly fuel. Nuclear electric is often pitched as the next step after nuclear thermal. Instead of heating propellant directly, the reactor makes electricity for high ISP thrusters. In theory, this bridges the gap between efficiency and usable thrust, and it sounds like the best of both worlds. In practice, the bridge is built from radiators, power electronics, and heavy shielding. Electricity must be conditioned, converted, and distributed, and each step adds losses that become heat. The reactor may be compact, but the system around it tends to sprawl. A reactor that produces megawatts in space is not just a reactor. It is a thermal management system that must survive micrometeoroids and years of cycling. It must also remain stable under changing loads, because thrust demands can vary while the reactor prefers steady operation. The radiator requirement is not a detail, it is a primary design driver. As power rises, radiator area rises, and the spacecraft becomes a heat rejection machine. On screen, you can picture long, dark panels unfolding like the ribs of a mechanical creature, oriented to avoid heating the rest of the vehicle. There is a deeper reason radiators are so punishing. Radiated power scales with temperature to the fourth power, so modest temperatures require enormous area. You can run radiators hotter to shrink them, but hotter radiators stress materials and threaten nearby systems. Nuclear electric also inherits programmatic risk. Launch approval, international treaties, public perception, and cost can cancel a design before metal is cut. Even if a reactor is never turned on until it reaches space, the mere presence of nuclear hardware changes the mission's political orbit, so nuclear propulsion is plausible but not magical. It can bend the curve for solar system missions, yet it cannot buy interstellar travel on human timescales. It is a way to pay less for the same trip, not a way to make the bill disappear. At this point, the conversation usually leaps to fusion, because fusion is the energy source that powers stars. It sounds like the clean answer to the energy bill. The word itself carries a promise: small fuel mass, vast energy, and a future that feels inevitable. Fusion promises extraordinary energy density and high exhaust velocity. It suggests a ship that carries little fuel and still reaches extreme speeds. In artwork, the exhaust becomes a luminous spear, and the vehicle looks less like a rocket and more like a moving power station. But fusion is hard on Earth for reasons that do not disappear in space. You must heat fuel to extreme temperatures, confine it, and extract net energy reliably. In plain language, you must hold a tiny artificial star without letting it touch the walls. On Earth, the best experiments are still wrestling with stability, materials damage, and continuous operation. A lab device can be serviced, a spacecraft cannot. When a test chamber is damaged, engineers replace components, but a deep space engine must endure without hands. In space, ignition and confinement become even more unforgiving. You need magnets, lasers, or pulsed compression systems that survive vibration, radiation, and fatigue. Each approach implies different machinery, and each machine has failure modes that scale with power. Magnetic confinement concepts demand strong superconducting magnets. Those magnets must be cooled, protected from radiation, and kept stable against quenching. The irony is sharp. Your engine produces immense heat, yet parts of it must remain extremely cold. Inertial confinement concepts rely on rapid pulses and precise timing. That means repeated shocks, repeated thermal cycling, and repeated mechanical stress. A spacecraft cannot tolerate a delicate alignment drifting out of spec after millions of pulses. Fuel handling is another hidden wall. Deuterium is manageable, but many high-performance concepts want tritium, which is scarce, radioactive, and difficult to store. Tritium also decays, which means your fuel inventory changes with time, and that complicates long missions. Aneutronic fuels like helium-3 sound attractive because they reduce neutron damage. They also demand even higher temperatures and fuel supplies we do not have. The Moon and the giant planets are often mentioned, but available somewhere is not the same as available at scale. Even if the physics works, the engine is not just a plasma. It is a nozzle problem, a materials problem, and a control problem at power levels that melt mistakes. Directing fusion products into thrust requires magnetic nozzles or other schemes that must handle extreme particle energies. Neutrons and high-energy particles punish structure. They embrittle metals, activate components, and force shielding that adds mass and reduces performance. Over time, a vehicle can become its own radiation source, which complicates maintenance and crew safety. Then the thermal problem returns in a new form. A fusion engine that produces gigawatts must reject waste heat, and radiators scale brutally with power. Even if much of the energy becomes directed exhaust, inefficiencies still become heat, and heat still must leave. Fusion also has a readiness gap that is easy to underestimate. A concept can be physically allowed and still be decades from a flight-qualified system. Space hardware must survive launch loads, vacuum, and long dormancy, and those requirements often break elegant laboratory assumptions. So fusion is not science fiction, but it remains pre-engineering. It is a promise without a production line, and timelines are measured in generations. The question is not only whether fusion can work, but whether it can work reliably, repeatedly, and cheaply enough to build more than one. If fusion is the dream of controlled fire, antimatter is the dream of pure conversion. Matter and antimatter annihilation offers unmatched energy density in theory. It is the closest thing in physics to turning mass directly into energy on demand. In equations, antimatter looks like the ultimate fuel. A small mass could release energy comparable to nuclear arsenals, and the rocket equation seems to relax. The numbers tempt us because they are so clean, and because they seem to bypass the slow climb of incremental improvement. In reality, antimatter is not a fuel we can stockpile. We can produce it only in vanishingly small quantities, at enormous energy cost and complexity. Particle accelerators can create antiprotons, but they do so as rare byproducts of violent collisions. Production is not just expensive, it is inefficient. You spend vast electrical energy to make tiny amounts, and most of that energy becomes heat and losses. If you imagine a factory for antimatter, you're really imagining a civilization-scale power sink with microscopic output. Storage is the next wall, and it is nearly absolute. Antimatter cannot touch normal matter, so it must be held in electromagnetic traps with extreme stability. Those traps require ultra-high vacuum, precise fields, and careful control because any contact is immediate annihilation. Those traps work for particles and small clouds, not for macroscopic fuel masses. Scaling from nanograms to grams is not an incremental step, it is a new regime. The fields must be stronger, the volumes larger, and the failure tolerance essentially zero. Even if storage were solved, the failure modes are catastrophic. A containment glitch becomes an explosion, and the safety case becomes politically unthinkable. A crewed mission would be asked to live beside a fuel tank that cannot be allowed to touch its own walls. Antimatter also does not solve the power handling problem. Converting annihilation energy into directed exhaust without destroying the engine is an unsolved challenge. High-energy gamma rays and energetic particles do not politely flow into a nozzle, and shielding against them adds mass quickly. So antimatter remains a theoretical upper bound, not a near-term path. It is the cleanest example of physics allowing something that engineering cannot host. It teaches a sobering lesson. Energy density alone is not propulsion, because propulsion is also control. When onboard energy becomes too heavy, the obvious move is to move the energy source off the spacecraft. Beamed propulsion tries to pay the energy bill from home. It is an audacious reframing. Turn the ship into a receiver, and turn the planet into the engine. A laser or microwave array pushes a sail, transferring momentum without carrying reaction mass. This attacks the rocket equation at its root, and that is why it fascinates. The spacecraft becomes less like a rocket and more like a mirror, riding a river of photons. For small payloads, the numbers can look surprisingly good. A gram-scale probe could be pushed to high fractions of C if the beam is powerful enough. In visuals, the sail is a thin, shimmering sheet, and the beam is a bright column that narrows into the distance. But the infrastructure is the wall. A planet-scale phased array demands extraordinary power generation, optics, cooling, and coordination over long periods. The array must act like a single instrument, with timing and phase control across vast distances on the ground. Beam physics also imposes a constraint that feels almost cruel. Diffraction makes beams spread, so keeping the spots small at long range requires a very large aperture. The farther you want to push, the more the transmitter must grow until it becomes a landmark visible from orbit. Pointing is also a brutal constraint. The beam must stay locked on a sail that becomes a distant speck, and tiny errors waste energy and miss the target. The sail is accelerating, the transmitter is rotating with Earth, and the atmosphere can distort the beam unless you build in space. Sail materials face competing requirements. They must be ultralight, highly reflective, heat-tolerant, and mechanically stable under intense acceleration. If they absorb too much energy, they overheat, and if they wrinkle or tear, they lose the very shape that makes the beam useful. Even if acceleration works, deceleration is the unresolved half of arrival. A beam from Earth cannot easily slow a craft at Proxima, because the geometry reverses. The sail that was a perfect receiver on the way out becomes a liability when you need to shed speed far from home. You can imagine a second array at the destination, but that assumes prior infrastructure. You can imagine magnetic braking against interstellar plasma, but the medium is thin. The interstellar environment is not empty, yet it is sparse enough that braking devices must be enormous to matter. So beamed sails trade onboard mass for civilization-scale construction. They convert a spacecraft problem into a planetary engineering project with long-term commitment. The question becomes cultural as much as technical. Can a society sustain a single, precise project for years without interruption? Across all these options, the pattern is consistent. If the engine is efficient, it is power-limited and slow. If it is powerful, it is heavy, hot, and complex. The trade is not a flaw in our imagination, it is a consequence of momentum and energy accounting. Every concept that looks like a shortcut simply moves the bottleneck. The bottleneck becomes radiators, or shielding, or fuel supply, or political permission, or buildable scale. When you chase one limit away, another appears, often in a form that is harder to miniaturize. This is the propulsion reality check. The laws of physics do not forbid reaching Pluto or Proxima, but they price speed in systems we cannot yet field. The price is not paid only in fuel, but in the supporting architecture that keeps the engine alive. For Pluto, advanced propulsion could shorten timelines and enable orbiters, but only with major investments in nuclear power and long-duration reliability. The difference between a flyby and an orbiter is not romance, it is delta V, and delta V is a demand for energy and mass. For Proxima, the gap is still immense. The propulsion options that might reach it demand either fusion we cannot sustain, antimatter we cannot store, or beams we cannot build. Even if the engine existed, the mission would still face decades of cruise, navigation over light years, and an arrival that cannot be improvised. So the dream remains ahead of the hardware. The difference between a concept and a mission is not imagination. It is mass budgets, heat budgets, and institutions. It is also testing, because deep space does not forgive prototypes that only work on a good day. And that returns us to the central question, with sharper edges. What limits make fast travel effectively impossible today, and what breakthroughs could change the invoice? Are we waiting for a new energy source, a new materials class, or a new willingness to build vast infrastructure in the dark? Next, we follow the consequences beyond engines. Even if propulsion was solved, the travelers in the spacecraft must survive acceleration, radiation, isolation, and time. Chapter 5 tested propulsion against physics and engineering, and the verdict was sobering in its clarity. Chapter 6 tests the same ideas against a constraint people feel in their bones: time. Time is the barrier that turns distance into a life decision, because it converts a line on a map into years of exposure. We have touched the moon, landed robots on Mars, and sent a probe beyond the planets into the dark. In archival footage, rockets bloom into white fire, and a tiny capsule rides a pillar of exhaust. Yet Pluto still takes years, and Proxima Centauri still measures itself in generations. The central question sharpens here with no room for romance. What limits of physics, biology, and reliability keep within a lifetime out of reach? Start with the simplest equation that everyone understands, because it refuses to negotiate. Travel time is distance divided by speed, and the universe is not shy about distance. Pluto sits a few light hours away in straight-line terms, but it is billions of kilometers by real trajectory. Proxima is 4.24 light-years away, which is about 40 trillion kilometers, and that number is not symbolic. It is a literal count of space your vehicle must cross while everything on board keeps working. On screen, the solar system shrinks to a pale diagram, and the outer planets become tiny beads. Then the camera pulls back again, and the sun becomes one star among many, almost lost in the Milky Way's haze. That visual zoom is the first lesson of time. Our intuition evolved for fields and coastlines. Interstellar distance is not just farther, it is a different category of scale. New Horizons is our honest benchmark for fast in the solar system, because it actually flew. It reached Pluto in about 9.5 years, and it never tried to stop. Its cruise speed was only tens of kilometers per second, which is impressive and still tiny. That speed is also deceptive because it was achieved with a launch boost and a Jupiter gravity assist. Even then, The spacecraft spent most of its journey coasting, cold and silent, while its radioisotope power source slowly weakened. There is historical context hidden in that cruise, because the solar system has always demanded patience. Voyager 2 took more than a decade to reach Neptune, and its famous images arrived as slow radio whispers. Cassini took nearly 7 years to reach Saturn, and it needed multiple flybys to reshape its orbit. These missions were triumphs of planning across administrations, budgets, and changing technology. They also show how years is already normal when the target is only a few billion kilometers away. Now scale that speed to a star, and the numbers stop feeling like missions. At roughly 15 kilometers per second, Proxima is not a mission, it is a mythic timeline. You're looking at tens of thousands of years, long enough for languages to change and nations to vanish. That is what orders of magnitude too slow means in human terms. It means your spacecraft becomes an archaeological artifact long before it becomes a scientific instrument. So we reach for fractions of light speed, because only those numbers compress light years into something a human calendar can hold. The arithmetic is clean and cruel, because it is just division. At 0.1 c, 1% of light speed, Proxima takes roughly 424 years without counting acceleration and braking. At 0.0 c, it is still about 85 years of coasting, which already strains the meaning of a single career. At 0% c, the trip is about 42 years of pure cruise, again before you pay for speeding up and slowing down. Those fractions of c sound small, but they are enormous in energy terms. Kinetic energy rises with the square of speed, so doubling speed roughly quadruples the energy you must supply and later remove. At 0.1 cm, you are not merely going fast, you are carrying a vast reservoir of motion. That motion becomes heat and damage if anything goes wrong, because even a dust grain becomes a projectile at relativistic speed. Time is not only the calendar, it is the safety margin you need to manage that energy. That sounds like a lifetime mission, until you add the parts that schedules always hide. You cannot teleport to 0.1 c, and you cannot arrive at 0.1 c and call it safe. The two burns problem returns as a time problem, because every realistic mission has phases. You accelerate, you coast, and you decelerate, and each phase has its own demands. A chart of velocity over time looks simple, but the machinery behind that curve is anything but. Even optimistic propulsion concepts do not change the calendar as much as people expect, because they collide with mass and reliability. A beamed sail might accelerate a tiny probe quickly, but a crewed ship cannot be a gram-scale wafer. The sail must survive micrometeoroids, remain pointed with extreme precision, and endure intense illumination without tearing. Fusion might raise exhaust velocity, but it still must push mass, manage heat, and survive decades. The time barrier is not only about reaching speed, it is about sustaining a mission long enough to matter. Now define what within a lifetime really means, because it is not just a number on a travel poster. It is not only the cruise age at launch and arrival, or the headline cruise time. It includes training years, mission preparation, and the time needed to build and test a vehicle that cannot be rescued. A mission that arrives in 40 years might still consume 60 years of a human life, once you count selection, rehearsal, and recovery. Even for robotic missions, the institutional lifetime matters, because teams retire and programs end. Then add the biological constraint that sits under every heroic timeline, quietly vetoing the boldest trajectories. Humans are not payloads that can be shaken, squeezed, and baked without consequence. Acceleration is felt as weight, and sustained weight changes circulation, breathing, and injury risk. High acceleration is a shortcut for time, but it is paid for in physiology. The body has tolerances, and those tolerances become design requirements. A fighter pilot can tolerate high G for minutes, with training and support, because the exposure is brief, and the mission ends quickly. A deep space crew cannot live at multiple G for days without severe strain, especially when sleep, nutrition, and medical care are limited. Even 1 G for long periods is not a casual choice, because it demands continuous thrust and enormous propellant or power. Comfortable acceleration is closer to a fraction of G, and that stretches the timeline. In a spacecraft, comfort is not luxury, it is a risk control. Acceleration also consumes distance, which is easy to miss when you only think in terms of speed. If you accelerate for a long time, you spend a large part of the journey just changing velocity. If you accelerate halfway and decelerate halfway, the midpoint is not a place, It is a turning point on a long curve. The ship's path becomes a smooth arc through space-time, and the cruise phase can shrink or vanish. For interstellar distances that can be fine, but only if you can sustain thrust for years. Consider a gentle acceleration like 0.01 g, about 1/100th of Earth gravity, which feels manageable. It is slow in the way that matters, because speed accumulates reluctantly at that level. It takes about a year to reach roughly 0.01 c, and about 10 years to reach roughly 0.1 c. Those years are not free because the ship is burning, heating, vibrating, and aging the whole time. Every valve cycle and every thermal expansion becomes part of the story. If you push harder to save time, the crew pays in stress and risk, and the structure pays in fatigue. If you push softer to protect the crew, the calendar expands and the ship must survive longer. Time becomes a lever that always pushes back no matter where you place your hand. The mission designer is trapped between human comfort and mission duration, and both sides are unforgiving. This is why just accelerate at 1g is a fantasy unless you can afford the power and mass. The constraint is even sharper when you remember that acceleration must be matched by deceleration, because arrival is part of the mission. A ship that arrives at Proxima 0.1 c cannot simply break with air, because there is no guaranteed atmosphere to catch it. If it does not break, it is a flyby at interstellar speed, not a visit. The target system flashes by like a roadside sign at highway speed, except the highway is a vacuum. If it does break, it must carry or access a braking method that works after decades. This is where time and propulsion merge into a single systems problem, because every phase must be planned for endurance. Long acceleration phases demand engines that run reliably for years, not minutes. Long coasts demand navigation and attitude control that remain stable for decades, while sensors drift and gyros age. Long deceleration demands a second act that cannot be improvised when the destination finally grows bright. A failure late in the mission is not a setback, it is the end. Now bring the discussion back to Pluto, because Pluto is the near case that still teaches the same lesson. A faster Pluto mission is not only a bigger rocket, it is a tighter schedule for every subsystem. If you want to arrive quickly and also stop, you multiply delta V, and you multiply time spent thrusting. The quick mission can become a longer propulsion campaign, even if the calendar looks shorter on paper. In the visuals, the spacecraft's trajectory bends and loops, showing how gravity assists trade time for fuel. Stopping is the quiet difficulty that headlines often ignore because stopping is expensive. New Horizons could afford to fly past Pluto because the science goals were designed around a brief encounter. A mission that wants orbit must carry the ability to shed speed at the end, which means propellant, power, or clever braking. Each option adds mass, and mass slows acceleration, and the loop closes again. Time is not a single barrier, it is a feedback system. Time also changes how we think about life support, because humans cannot be treated like durable cargo. For probes, time is mostly electronics aging and power fading, plus the slow accumulation of radiation damage. For humans, time is consumables, recycling, and the slow accumulation of small failures. Life support is not a box you add, it is a living system you must keep stable. In a long mission, life support becomes the central engine of survival, running every second. A closed-loop ecosystem sounds elegant because it promises to recycle air, water, and nutrients with minimal resupply. In practice, it is a web of chemical processes, filters, sensors, pumps, and biological components. Each part has a lifetime, and each lifetime becomes a schedule that must be managed. Over decades, maintenance is not a task, it is the mission. The crew becomes part engineer, part biologist, and part custodian of invisible balances. Food is not just calories, it is storage, variety, and nutrition stability across years of monotony. Vitamins degrade, fats oxidize, and packaging fails under radiation and thermal cycling. Even the smell and texture of food matters, because morale is a physiological variable. You can grow food, but that adds light, water, microbial control, and agricultural redundancy. Every kilogram of resilience is another kilogram that must be accelerated and protected, and every plant system is another set of failure modes. Water recycling must be nearly perfect, because resupply is impossible and loss is cumulative. Urine processing, humidity capture, and purification systems must run for years without catastrophic contamination. Biofilms can form in tubing, filters can clog, and sensors can drift until they lie. Air revitalization must remove carbon dioxide, trace toxins and particulates while keeping oxygen stable. If any loop drifts, the crew becomes the warning sensor and the warning arrives late. Spare parts are the quiet mass that time demands, and they hide in every long-duration plan. A 10-day mission can accept a few single-point failures because rescue is possible and exposure is brief. A 50-year mission must assume that almost everything will fail at least once, and some things will fail repeatedly. Redundancy becomes a philosophy, and the ship becomes a warehouse of replacements. The inventory must be curated like a library, because the wrong spare is dead weight. Then there is the math of compounding probability, which is cold but honest. Even if each subsystem is highly reliable, the number of subsystems is large, and the mission duration is long. Small failure rates accumulate into near certainty over decades, because time multiplies opportunity for error. Reliability engineering becomes a battle against statistics, fought with margins and monitoring. The ship must be designed to fail gracefully, not perfectly. Maintenance itself is a hazard, because repairs are never free of risk. Repairs require tools, training and time, and they create opportunities for mistakes. A crew in deep space cannot call a technician and cannot order a replacement overnight. Every repair is performed under fatigue, confinement, and the knowledge that there is no outside help. In that environment, even routine work acquires the tension of surgery. Radiation exposure is part of the time barrier, even before we reach the next chapter's deeper focus on hostility. Galactic cosmic rays and solar storms do not care about morale or schedules. The longer you travel, the more dose you accumulate, and shielding mass grows quickly. Time turns invisible particles into a cumulative injury, because dose is integrated over months and years. The visual is subtle, a quiet hull and a constant rain of energetic particles passing through. Microgravity also taxes the body over time, and we have decades of orbital experience to prove it. Bone density drops, muscles weaken, and the cardiovascular system adapts in ways that can be dangerous on arrival. The body's efficient, and it sheds what it does not need, which becomes a problem later. Artificial gravity could help, but it adds rotating structures, bearings, vibration, and new failure modes. Again, time multiplies the engineering, because moving parts must keep moving without wearing out. Now shift from biology to psychology, because the mind is also a life support system. Isolation is not only loneliness, it is the loss of novelty and the loss of exit options. A crew that cannot leave cannot reset conflict by walking away, and there is no private world beyond the walls. Over years, small tensions can become structural threats, like cracks spreading through metal. The ship's interior becomes a landscape, and every corridor carries memory. Communication delay makes isolation sharper because it removes the simplest comfort: immediate response. Even within the solar system, delays are minutes to hours, and real-time conversation disappears. At Proxima, messages take over 4 years one way, and replies take more than 8. Advice from Earth becomes history by the time it arrives, and the crew becomes its own mission control. The psychological weight is profound. You are responsible, and you are alone in time. Crew dynamics must be designed, not hoped for, because goodwill is not a control system. Selection, training, and culture matter as much as hardware, and they must be built for endurance. You need conflict resolution, shared purpose, and routines that survive boredom, grief, and fear. The rituals of daily life become stabilizers, like gyros keeping a spacecraft pointed. A mission can fail without a single mechanical breakdown, simply by losing cohesion. Then comes the sociological cliff, where the mission stops being a voyage and becomes a society. If the trip is longer than a working lifetime, you face a generational mission. Children may be born aboard, and they did not consent to the voyage. Education, governance, and justice become onboard systems, and they must function without external authority. The ship's rules are no longer procedures, they are laws. A generational ship also changes what arrival means, because arrival becomes a story told to descendants. The people who launch are not the people who land, and the mission becomes a moving society with its own identity. That society must manage inequality, mental health, reproduction, and leadership succession. The ship becomes a world, and worlds have politics, even when they're enclosed in metal. What happens when the mission's purpose fades or splits into factions? Even without children, a multi-decade mission raises ethical questions that do not disappear with enthusiasm. Is it acceptable to send a crew on a journey they are unlikely to complete, even if they volunteer? Is it acceptable to accept high probabilities of cancer, isolation trauma, or system failure because the destination is inspiring? The romance of exploration becomes a contract written in risk, and the fine print is measured in years. The question is not whether humans are brave, but whether the design is just. Robotic missions avoid many of these costs, but they do not erase the time barrier, they simply relocate it. A probe can wait, but science has its own deadlines, and technology becomes obsolete. A mission that returns data after a century is hard to fund, hard to maintain institutionally, and hard to integrate into a living scientific community. The people who ask the question may be gone when the answer arrives. Time becomes a political variable, not just an engineering one. This is why Pluto still matters in a chapter about lifetimes, because it is the closest rehearsal of the same dilemma. Pluto is reachable, but quickly is expensive, and safely adds more years and more mass. Proxima is reachable in physics, but not in the time budgets that human bodies, institutions, and politics can reliably sustain. The gap is not imagination, it is compounded constraints. Each constraint is manageable alone, but together they form a wall, so the time barrier is not a single number, and it is not solved by optimism or a single breakthrough. It is a stack of clocks running at once, each one ticking in a different domain. The propulsion clock measures acceleration and braking, and it punishes mass. The biology clock measures dose, degeneration, and stress, and it punishes duration. The engineering clock measures wear, corrosion, and random failure, and it punishes complexity. The social clock measures cohesion, consent, and continuity, and it punishes isolation. When we ask why reaching Pluto quickly or Proxima within a lifetime is still impossible today, this is the answer's most human layer. The universe is not only far, it is slow to cross safely, and safety is not optional. Speed demands energy, but survivable speed demands time management across every subsystem. The deeper question lingers like a quiet echo. How much time can a civilization commit and still remain itself? And even if we accept long timelines, the next truth waits outside the hull, patient and indifferent. Interplanetary and interstellar space is not empty, and its hostility is not theoretical. The longer the exposure, the more lethal the environment becomes. Radiation, impacts, and thermal extremes accumulate like interest. Even if we accept long timelines, interplanetary and interstellar space is not empty. It is hostile. That is where the story goes next. Chapter 6 ended with a simple warning, and it lands harder the farther we look outward. Even if we accept long timelines, the space between worlds is hostile. In the inner solar system, that hostility is episodic, and partly shielded by Earth's magnetic field and thick atmosphere. On the surface, most radiation hazards are filtered, scattered, or absorbed before they reach living tissue. In low Earth orbit, astronauts still benefit from Earth's magnetosphere, although they also pass through regions like the South Atlantic anomaly, an indentation in the magnetic field where trapped particles dip closer to spacecraft. Beyond Earth's magnetosphere, that shielding is gone, and the exposure becomes a mission driver. The visuals change as well. The planet shrinks into a bright coin, and the protective cocoon around it becomes an invisible boundary you can cross in hours. Past that boundary, the environment stops being background scenery and becomes an active participant in mission design. Radiation is the first invisible hazard that scales with distance, duration, and speed, and it is not one thing. It is a stack of particle populations with different energies, timing, and biological consequences. Some arrive in violent bursts, others arrive with metronomic persistence, and a few are shaped by magnetic fields that we barely notice until they fail us. Start with the Sun, because it is both our power source and our nearest threat. Solar energetic particles erupt from flares and coronal mass ejections, when magnetic field lines in the solar corona snap and reconnect. Those events can accelerate protons, electrons, and heavier ions to near-relativistic speeds. They arrive fast, spike hard, and can deliver dangerous dose in hours. A solar particle event is not just more radiation in a general sense. It is a sudden flood of charged particles that can overwhelm shielding assumptions and saturate detectors. The crew might see nothing outside the window, yet instruments would register a sharp rise. like a Geiger counter turning from clicks into a continuous hiss. Solar particle events are not constant, which makes them harder to design around. You cannot schedule them, and you cannot outrun them with today's propulsion. Even if you had a faster ship, the particles are already moving at a significant fraction of light speed. You can only detect them, shelter, and hope your warning time is real. That warning time is itself a technical problem. Some alerts come from observing the sun, but the most dangerous particles can arrive before a clear optical signature appears. Space weather forecasting has improved since the early days of crewed flight, yet it still carries uncertainty that no checklist can fully remove. The question becomes uncomfortable. How much risk is acceptable when the storm may already be on its way? The second source is galactic cosmic rays, which are the opposite of a storm. They are a persistent drizzle of high-energy nuclei from supernova remnants and other violent astrophysical accelerators. Their exact origins span multiple sources, including shock waves in expanding supernova shells and possibly jets from distant active galaxies. They are fewer in number than solar particles, but far more penetrating. Cosmic rays are not stopped by a thin hull, and they do not politely deposit energy at the surface. They punch through structure, ionize tissue along long tracks, and create cascades of secondary particles inside the spacecraft. In radiation physics, this matters because dose is not only about energy, but about how that energy is delivered. Dense ionization tracks can be disproportionately damaging. Some cosmic ray particles are heavy ions, stripped nuclei of elements like carbon, silicon, or iron. These are sometimes called HZE particles, high charge and energy, and they behave like microscopic cannonballs. They can pass through multiple layers of material, leaving a trail of molecular disruption that biology struggles to repair. Even when the average dose seems manageable, the quality of the radiation can make the risk more severe. For interstellar travel, there is a third framing that changes the baseline. Outside the heliosphere, the sun's magnetic bubble no longer modulates the incoming flux as strongly. The heliosphere is shaped by the solar wind, and it acts like a vast dynamic shield that deflects some charged particles. When probes like Voyager crossed its boundary, they revealed a transition into a different radiation regime. Still not a wall, but a shift in the background. Beyond that boundary, the background becomes more constant, and the mission loses a layer of natural protection. The ship is no longer travelling inside a familiar magnetic weather system. It is moving through the local interstellar medium, where the shielding is mostly whatever the spacecraft brings with it. The visuals are stark. The sun becomes just another bright star behind you, and the protective influence of home fades into mathematics. This is where the documentary's central question tightens again. We can imagine engines that reach Pluto faster, or probes that sprint toward Proxima. The environment then charges interest on every day and every kilometre. The universe does not care whether a mission is heroic or routine, because physics bills everyone the same. Dose is an accounting problem that biology cannot ignore. Radiation risk accumulates with time, and high-speed missions still require long exposure unless acceleration and braking are extreme. Even a perfect cruise trajectory cannot erase the integrated dose. The body keeps the receipts written in DNA breaks, altered cells, and repair processes that are never perfectly clean. For crews, the consequences are not abstract, and they are not only long-term. Increased cancer risk is the headline, but not the whole story. High-energy particles can damage the central nervous system, degrade cognition, and complicate mission performance long before any diagnosis. That is a chilling thought for deep space, where judgment, attention, and emotional stability are part of the life support system. Radiation can also affect the cardiovascular system, the immune response, and the eyes, where astronauts have already experienced vision changes during long missions. In deep space, those effects would unfold without quick evacuation and without the medical infrastructure we take for granted on Earth. The ship becomes a clinic as well as a vehicle, and the clinic has no specialist to call. For embryos and children, the risk picture is harsher, which matters for any generational concept. Developing tissue is more sensitive to radiation-induced damage, and the long horizon of a lifetime increases the chance that early injury becomes later disease. For adults, the risk is still mission-limiting because it competes with every other safety margin. Biology becomes a technology constraint, not a medical footnote. Robotic spacecraft do not get cancer, but they still suffer radiation injury. Electronics accumulate total ionizing dose, and single particles can flip bits in memory or logic. A mission can fail from a microscopic event that leaves no visible scar. In deep space, a single corrupted command can be the difference between a stable cruise and a slow, silent drift. Engineers already fight this in Earth orbit and deep space, and the history is instructive. Early satellites discovered that radiation could trigger phantom commands and unexplained resets, and modern missions still log these events as part of routine operations. They use radiation-hardened components, error-correcting memory, watchdog timers, and redundant computers that vote on reality. Those techniques help, but they cost mass, power, and performance. As missions stretch from years to decades, the reliability math becomes brutal. You cannot assume a reset fixes everything, because the hardware itself degrades. A bit flip is recoverable, but a damaged transistor is permanent. Over time, margins shrink, timing drifts, and the system becomes less like a machine and more like an aging organism. Now the shielding problem arrives, and it is not solved by wishing for thicker walls. Physical shielding works by adding mass between you and the particles, which increases the chance they lose energy before reaching sensitive systems. Mass is exactly what Propulsion chapters showed is expensive to accelerate and even more expensive to break. Every kilogram of shielding is a kilogram that must be pushed, guided, and eventually slowed. For solar energetic particles, shielding can be practical because energies are lower than the most extreme cosmic rays. A well-designed shelter can cut dose dramatically during a storm, especially if it uses hydrogen-rich materials that are efficient at slowing charged particles. The hard part is guaranteeing that the crew can reach it quickly and that it stays usable after years. A shelter that is blocked by cargo or compromised by a leak is not a shelter at all. For galactic cosmic rays, shielding becomes a trap if it is done naively. High-energy nuclei can strike shielding atoms and produce secondary radiation, including neutrons and gamma rays. Add too much dense material, and you can reduce one component while increasing another inside the cabin. The shield becomes a factory for new particles, and the crew sits downstream of the production line. This is why shielding is not simply thickness. It is composition, geometry, and where you place the mass you already need. The best shield is often the mass you cannot avoid carrying anyway, arranged with intention rather than convenience. The spacecraft becomes a three-dimensional puzzle, where plumbing, storage, and human space must interlock with radiation physics. Water is a favourite example because it is already required for life support, hygiene, and thermal control. Hydrogen-rich materials slow charge particles more efficiently per kilogram than heavy metals, and they tend to produce less harmful secondary radiation. A spacecraft can wrap tanks around a habitat and call it dual-use structure. In a well-designed layout, the crew's sleeping quarters might sit behind the thickest water walls, quiet, dim, and comparatively safer. Food, waste, and supplies can be treated the same way, and the logic is almost poetic. The ship becomes a layered system where logistics are also protection, and where yesterday's meals become tomorrow's shielding. This is elegant in concept, but it demands careful planning because the shield is consumed over time. If the mission eats its own armour, then the protection strategy must evolve with the inventory. Storm shelters are the most credible near-term compromise for crews. You accept that you cannot block everything, then you build a small volume with the highest practical shielding. When the sun erupts, the crew rides out the spike like sailors below deck. The imagery is claustrophobic by necessity. A tight compartment, knees tucked, instruments glowing, and the knowledge that the storm is outside the hull. Magnetic shielding is the other tempting idea, because it promises protection without heavy mass. In principle, a magnetic field can deflect charged particles the way Earth's magnetosphere does, bending their paths so they miss the habitat. In practice, the field strengths and volumes required are enormous, especially if you want to protect a large living space rather than a small capsule. The field must also be shaped and stable, because gaps and weak regions become funnels. A useful field implies large superconducting coils, cryogenic systems, and structural support against magnetic forces. Those systems add mass and complexity, and they introduce new failure modes that cannot be repaired easily. They also do little against neutral particles like neutrons, which do not respond to magnetic fields. The dream of a weightless shield collides with the reality of engineering: cold, heavy, and unforgiving. Electrostatic shielding faces similar problems with additional risks. High voltages in a plasma environment can cause arcing and charging can attract dust or interfere with sensors. A shield that fails catastrophically is worse than a shield that is merely heavy. In deep space, A dramatic failure is not a spectacle, it is a mission-ending event. So the trade becomes stark, and it echoes every other constraint in spaceflight. If you shield with mass, you pay in propulsion and launch infrastructure. If you shield with fields, you pay in power, cryogenics, and reliability across decades. The mission is forced to choose which bill it can afford to pay. This is the point where the chapter connects back to propulsion in a new way. High-speed travel reduces calendar time, but it increases the energy stored in motion. That energy turns the environment into a weapon. The faster you go, the more violently you interact with what would otherwise be harmless. Radiation is one weapon, because higher speed can change how often you encounter certain regions and how you time solar cycles. Interstellar dust is another, and it is the hazard that makes speed feel like a dare. In the quiet blackness between stars, the smallest grain can become the loudest impact. In the inner solar system, micrometeoroids are already a known threat. They pit surfaces, crack thermal blankets, and occasionally punch holes in radiators. Engineers study impact craters on returned hardware, and they model debris flux the way meteorologists model rain. Most missions survive because relative speeds are manageable and exposure times are limited. At interstellar cruise speeds, the same grains become catastrophic. Kinetic energy scales with the square of velocity, and at a significant fraction of light speed the numbers explode. A speck of dust carries the energy of a bullet, or worse, depending on speed. The physics is simple, but the implications are brutal. Speed turns dust into ordnance. Even at lower fractions, the problem is not a single impact. It is erosion over trillions of kilometers, a long-duration sandblasting that never takes a day off. Each grain removes a little material, and the cumulative effect can strip coatings, weaken structures, and degrade optics until the mission is blinded. The ship's forward face becomes a geological record of every collision it survived. Puncture risk is the acute version of the same story. A tiny particle can penetrate a pressure vessel or a propellant line if the relative speed is high enough. At interstellar velocities, you cannot rely on luck as a design philosophy. A single pinhole in the wrong place can turn a closed life support loop into a countdown. This is why spacecraft use Whipple shields, which sound simple and are not. A thin bumper layer sits ahead of the main wall, separated by a gap that gives physics room to work. The impact vaporizes the particle and spreads the energy into a wider cloud before it reaches the rear layer. Instead of one concentrated punch, the rear wall receives a dispersed spray. Whipple shielding works well for certain speed regimes, and it is widely used for orbital debris protection. For interstellar speeds, the design must be rethought because the plasma cloud itself is energetic. The shield becomes a sacrificial system that must survive long-term ablation. Over decades, the bumper is not just protection, it is consumable material. Some concepts propose a forward sacrificial shield, thick and replaceable in effect if not in practice. Others imagine a cloud of dust or gas released ahead of the craft to pre-vaporize incoming grains, turning discrete impacts into a more uniform interaction. Every approach adds mass, complexity, or propellant consumption. The ship must decide whether it carries armor, carries the means to regenerate it, or carries the means to blunt impacts before they arrive. The geometry problem is unforgiving, and it shapes the entire vehicle. You cannot shield every direction equally, so you must define a forward direction and keep it stable. That requirement ties dust protection to attitude control and navigation, and it punishes any tumbling or loss of pointing. A moment of instability can expose unarmored surfaces to the very flux the design tried to concentrate. The interstellar medium is thin, but thin is not zero when the path is light years long. Hydrogen atoms, helium, and dust grains become a constant sandblasting at high speed. The ship's nose is no longer just structure, it is a heat and impact management system, designed to take punishment without passing it downstream. Now return to electronics and materials, because radiation and dust do not only threaten life. They threaten the ability to function at all, especially when the mission timeline is measured in decades. The slow damage is the most dangerous kind, because it hides inside normal operations until it becomes a failure. Radiation causes displacement damage in semiconductors, changing how devices behave as atoms are knocked out of place. Solar panels degrade as their crystal lattices are disrupted, reducing power output year by year. Sensors drift, star trackers lose sensitivity, and calibration becomes a moving target. The spacecraft must keep measuring itself, because the instruments that measure the universe are also being changed by it. Materials also age under particle bombardment, and the effects are not always obvious at first glance. Polymers become brittle, adhesives weaken, and insulation cracks, especially when radiation is paired with thermal cycling. Metals can embrittle under radiation and repeated stress, and microcracks grow with vibration and time. The ship is always in motion, and motion always finds the weakest point. Thermal control surfaces are especially vulnerable because they sit exposed and must remain predictable. Coatings that manage heat can darken or erode, changing emissivity and absorptivity. A small change in thermal balance can cascade into overheating, which then accelerates degradation. In deep space, thermal control is not comfort. It is survival for electronics, propellants, and life support chemistry. For Pluto-class missions, this is already a concern because power is limited and repair is impossible. The spacecraft is far away, running on thin margins, and every subsystem depends on the others behaving as expected. For Proxima-class missions, it becomes existential because you're asking hardware to remain within spec for longer than many human institutions last. The mission must be designed to outlive its designers, its launch team, and perhaps the organizations that funded it. Redundancy helps, but redundancy also ages in the same environment. You can fly two computers, but both see the same radiation background and the same slow accumulation of damage. You can carry spares, but spares must survive storage and still work when finally needed. A spare that fails on first power-up is not a backup, it is dead mass. Software can correct some failures, and autonomy becomes mandatory as lifetime grows. Autonomy is not magic. It is code that must anticipate rare events without human intervention, while running on hardware that is slowly being damaged. The spacecraft must diagnose itself, isolate faults, and choose safe modes without waiting hours, days, or years for instructions. This is where biology becomes the limiting technology again, and the contrast is stark. A robot can be overbuilt and accept performance loss, limping forward with degraded sensors and reduced power. A human habitat must maintain narrow ranges of air, water, temperature, and microbial control. The crew cannot be rebooted, and the ship cannot be serviced. The chapter's awe is not in the cruelty of space, but in the precision required to survive it. We are not blocked by a single lethal wall. We are constrained by many small invisible hazards that add up across time. Deep space is not a monster that strikes once, but a constant pressure that tests every assumption. So the engineering question becomes layered, and each layer sharpens the next. How much shielding can we afford before propulsion becomes impossible? How much speed can we afford before dust becomes explosive? How much autonomy can we trust when the hardware is aging and the crew is exposed? Each question is answerable in isolation, yet the combined answer is where missions live or die. There are credible partial answers, and they look like compromises rather than miracles. Use storm shelters and smart mass placement for solar events, and accept that some exposure is unavoidable. Use rad-hard electronics and fault-tolerant architectures for long crews, and design for graceful degradation. Use sacrificial forward shielding and Whipple layers for dust, and treat the nose as a consumable interface with the void. But each partial answer has a price tag that compounds with mission ambition. More shielding increases launch mass and reduces acceleration, which can lengthen the trip and increase total dose. More redundancy increases complexity and power draw, which increases thermal demands and failure pathways. More speed increases impact energy, and makes every design margin thinner because the environment hits harder and faster. This is why reaching Pluto quickly is not just a propulsion problem. A faster trajectory reduces time, but it can increase radiation exposure during solar maximum if timing is unlucky. It can also increase encounter speeds that complicate capture and raise thermal loads. The mission becomes a choreography with the solar system's moving parts, and the timing matters as much as the thrust. This is why reaching Proxima within a lifetime is not just an energy problem. Even if you could accelerate a crewed ship to a fraction of c, you must keep bodies and machines intact while the universe throws particles and dust at relativistic closing speeds. The ship would be both a vehicle and a fortress, and the fortress would be aging as it travels. The documentary's central question now has a sharper answer, and it is not comforting. The void is not empty, and the hazards are not optional. They scale with distance, time, and speed in ways that make biology and reliability the limiting technologies. When we talk about reaching the stars, we're also talking about surviving the journey's invisible arithmetic. Transition. If survival is hard, steering is harder, because you must thread a safe path through a hostile medium. To manage radiation storms, you need early warning and correct orientation, because even a few degrees can change what mass sits between crew and particles. To manage dust, you need a stable forward shield and a predictable attitude, because the nose must face the oncoming flux. To manage aging systems, you need precise navigation that avoids wasting propellant on late corrections. Every unnecessary burn is lost margin, and margin is what hazards consume. That pushes us into the next barrier. Hazards are only manageable only if we can navigate precisely, so we turn to guidance, communication, and the profound difficulty of steering in deep time. Chapter 7 ended with a warning. Survival is hard and steering is harder. A fast ship that cannot aim is just a projectile, and deep space offers no guardrails. In the visuals, there is no road, no horizon line, only a black field where small errors hide. Navigation begins with a basic truth that Earth hides from us. In space, you do not know where you are by looking down. You infer your state from stars, radio signals, and physics models, then you live with the uncertainty those inferences leave behind. On Earth, we navigate by landmarks and maps, and even a cloudy day still gives us gravity and friction. In orbit or on an escape trajectory, there is no tactile feedback, only numbers, photons, and the slow accumulation of tiny biases. The spacecraft does not feel its motion, it estimates it. In the inner solar system, navigation feels routine because the infrastructure is mature. Ground antennas transmit, spacecraft transpond, and mission teams solve orbits with constant updates. That comfort fades with distance, time, and speed, because the loop between measurement and correction stretches and thins. This routine has a history, and it was earned the hard way. Early deep space missions learned to trust radio tracking and careful modelling, because even a small mismatch between prediction and reality could waste a once-in-a-lifetime encounter. By the time we were navigating to Jupiter and beyond, orbit determination had become a discipline with its own tools, standards, and hard-won instincts. A spacecraft's first tool is attitude knowledge, not position knowledge. Star trackers compare a camera image to a star catalogue and compute orientation. In a clean rendering, you see the tracker's field of view, pinpoint stars, a faint haze, and a computed quaternion that becomes the craft's sense of up. If the tracker is off by a fraction of a degree, every thrust points slightly wrong. That error does not announce itself with drama, it simply rotates the future. Over long coasts, a consistent mispointing becomes a slow, relentless sideways drift. Star trackers are precise because the sky is stable, but the hardware is not perfectly stable. Temperature changes flex structures by microns, optics age, and radiation can create hot pixels that masquerade as stars. Calibration tables help, yet every table assumes the instrument behaves tomorrow like it behaved last year. Gyroscopes and inertial measurement units fill the gaps between star tracker updates. They integrate rotation rates and estimate attitude continuously. They also drift, and drift becomes a silent error source over years, especially when updates are sparse or the star tracker is blinded by glare. That drift is not a single number, and it is not always linear. Biases can change with temperature, with aging electronics, and with cumulative radiation damage. The spacecraft must constantly reconcile two imperfect witnesses, one that is absolute but intermittent, and one that is continuous but forgetful. Position and velocity are usually anchored by radio tracking from Earth. Ranging measures round-trip light time to estimate distance. Doppler tracking measures frequency shift to estimate line-of-sight velocity, and those two measurements together form the backbone of deep space orbit determination. These methods are powerful because they turn the solar system into a measured geometry. They also depend on signal strength, stable clocks, and a cooperative spacecraft. As the probe gets farther, the measurements weaken and the update cadence slows, which means the model must carry more of the burden. Radio ranging is limited by timing precision and by the spacecraft's transponder performance. A nanosecond timing error is only 30 centimeters, which sounds small. Over interplanetary arcs, small errors couple into large trajectory uncertainties, because the orbit solution is a stitched narrative of many imperfect measurements. Even the simple act of timing a signal is layered with corrections. Engineers account for delays in electronics, in antennas, and in Earth's atmosphere, where water vapor can stretch the path. They also account for the fact that Earth itself is rotating and wobbling. Our reference frame is alive. Doppler tracking is exquisitely sensitive to velocity along the line of sight. It can detect millimeters per second under good conditions. It cannot directly see sideways motion, where a tiny angular mistake becomes a huge miss, and where the geometry is least forgiving. That sideways problem is the core geometry of deep space aiming. If your direction is wrong by a tiny angle, the miss distance grows with range. At interstellar distances, angular error is destiny, because the lever arm is measured in light years. A 1 arc-second pointing error is about 5 millionths of a radian. Over 1 light year, that becomes tens of millions of kilometers. Over 4 light years, it becomes a miss measured in planetary orbits, and the camera's target becomes empty sky. In a visual diagram, the cone of uncertainty looks harmless near the spacecraft. Far away, it blossoms into a vast circle that could swallow an entire inner system. The terrifying part is that the cone can grow without any single moment of failure. Even if the numbers vary with assumptions, the pattern is fixed. Linear error scales with distance, and distance is the one variable we cannot negotiate. The farther we go, the more the universe punishes small mistakes, and the more navigation becomes a fight against accumulation. This is why optical navigation becomes essential for many missions. Cameras track the apparent motion of target bodies against background stars. The spacecraft uses that motion to refine its trajectory estimate, turning images into geometry and geometry into a better future. Optical navigation works well when you can see a target as a resolved object. Near Jupiter or Pluto, moons and planets provide strong visual anchors. In interstellar cruise, there is no nearby landmark for most of the journey, only star fields that barely change. Interstellar navigation must rely on distant references and onboard inference. Star fields change slowly, and parallax is tiny. The spacecraft must detect minute shifts and trust its own calibration for decades, even as its sensors age and its optics collect microscopic damage. The parallax problem is subtle but brutal. From far away, nearby stars shift against distant ones by angles that can be smaller than a pixel. So the craft must know its own camera geometry, focal length, distortion, alignment, at a level that feels more like metrology than photography. In the solar system, we correct often because propellant is precious but available. New Horizons made small trajectory correction maneuvers, then coasted for years. Those corrections were planned with constant Earth-based orbit determination, and the mission could afford patience. At Proxima scales, correction philosophy changes. If you wait too long, the required correction grows beyond what you can afford. Early errors must be found early, which demands better sensing and better autonomy, because the best time to fix a drift is before it becomes a destiny. Navigation also depends on timekeeping, because time is position in a relativistic universe. Deep space ranging assumes stable clocks on Earth and on the spacecraft. Clock drift becomes another hidden angle that widens with distance, because the measurements are built from timestamps. Relativity is not a philosophical footnote here. Signals propagate at light speed, clocks tick at rates influenced by motion and gravity, and models must reconcile those effects to keep errors from masquerading as trajectory changes. The spacecraft may not feel relativity, but its navigation solution does. Pulsar navigation is often proposed as a deep space GPS. X-ray pulsars provide periodic signals that could act like cosmic lighthouses. In principle, timing several pulsars yields position fixes without Earth, using the galaxy's own clocks as reference beacons. In practice, pulsar nav requires sensitive detectors, careful modelling, and long integration times. It also adds mass, power draw, and failure modes. It is promising for autonomy, but it is not a simple replacement for Earth tracking, especially when the craft is small and power-starved. The promise is real though, and it is worth picturing. A detector counts X-ray photons, builds a pulse profile, and compares arrival times to predicted ephemerides. The craft is not seeing a lighthouse beam. It is doing statistics on sparse photons, then turning those statistics into a position estimate. All navigation methods share one uncomfortable dependency. They are only as good as the spacecraft's ability to observe, compute, and remain stable. If sensors degrade from radiation and dust, the navigation solution degrades with them, and the degradation may be gradual enough to evade alarms. Guidance is the next layer, and it is not the same as navigation. Navigation estimates where you are and where you're headed. Guidance chooses the desired path and computes the burns to stay on it, translating uncertainty into action. Control is the final layer, and it is where physics becomes operational. Control actuators rotate the spacecraft, fire thrusters, and manage momentum wheels. Control authority is limited by propellant, wheel saturation, and mechanical wear, and each limit becomes tighter over long durations. Momentum wheels, for example, store angular momentum like spinning flywheels. Over time, tiny torques from sunlight, thermal radiation, or outgassing can spin them up. When they saturate, the craft must dump momentum with thrusters, spending propellant just to stay pointed. At Pluto, a late burn can still rescue a flyby geometry. At Proxima, a late burn may be mathematically impossible. The mission becomes a one-shot chain of decisions with shrinking margin, and the chain begins long before the destination is visible as anything but a bright star. Now add the barrier that makes all of this feel like flying blind. Communication delay is not an engineering inconvenience. It is a hard limit set by the speed of light, and it turns distance into time that cannot be brought back. In the solar system, that delay is already large enough to change operations. The Moon is seconds away, but Mars is minutes away. Jupiter is tens of minutes away, and Neptune is hours away, which is long enough for a sequence to finish before you can intervene. Those minutes and hours erase real-time piloting. Spacecraft execute command sequences, then report results later. When something goes wrong, the diagnosis arrives after the event has already unfolded, like reading yesterday's weather report during today's storm. Mission control compensates with careful planning and safe modes. Spacecraft are designed to detect anomalies and protect themselves. They point antennas at Earth, reduce activity, and wait for instructions, often with a minimal heater and radio heartbeat that keeps them alive. That model breaks as we approach interstellar distances. At Proxima, a one-way message takes about 4.24 years. A question and answer loop takes nearly a decade, even if everyone responds instantly, and even if the spacecraft is still healthy enough to listen. Remote piloting becomes physically meaningless. You cannot steer around a hazard you learn about years later. You cannot troubleshoot a failing subsystem in a conversation that spans political terms and personal careers, because the people who ask the question may not be there for the answer. Emergency response becomes a tragic concept at that scale. A fault that threatens the mission must be handled on board. By the time Earth hears the alarm, the spacecraft has already succeeded or died, and the only thing left is a post-mortem. This forces autonomy from a convenience into a requirement. The spacecraft must detect failures, isolate them, and reconfigure itself. It must decide when to spend propellant, when to power down, and when to risk continuing, because hesitation can be as fatal as recklessness. Autonomy is not just software competence, it is a reliability promise across decades, on hardware that is aging. Every decision rule must be verified before launch, because you cannot patch with confidence later, and because a fix sent from Earth arrives long after the context has changed. Verification is uniquely hard because deep space failures are rare and diverse. You cannot test every combination of sensor drift, radiation upsets, and mechanical wear. You simulate, you analyze, and you accept residual unknowns. Then you launch anyway, because exploration has never been a zero-risk discipline. Fault detection and isolation must be conservative, because false positives can waste the mission. A safe mode that triggers too easily can stall science for years. A safe mode that triggers too late can lose the spacecraft, and the line between those outcomes is thin. Engineers often describe this as designing a nervous system. The craft needs reflexes that are fast and simple, and it needs higher-level reasoning that is cautious and context-aware. Yet both layers must run on limited power and limited compute, which means every added capability competes with survival basics. Self-repair is mostly a myth for small probes, and a nightmare for crewed ships. You can add redundancy, cross-strapping, and spare pathways. You cannot easily replace a cracked radiator or a damaged sail, and you cannot ask a distant machine to improvise new materials. Some missions may carry limited robotic maintenance capability. That adds manipulators, sensors, and control complexity. It also adds more components that can fail, which is the paradox of robustness. Every safeguard is also another thing to safeguard. The autonomy problem ties back to earlier chapters about time and hostility. Radiation flips bits and slowly degrades components. Dust impacts road surfaces and can blind optics, and the damage is often cumulative rather than catastrophic. A human team can diagnose subtle patterns with context and creativity. A spacecraft must do it with limited sensors and bounded computation. It must distinguish noise from danger without the luxury of hindsight, and it must do so while its own measurements become less trustworthy. Now the other half of communication arrives, and it is quieter than delay. Bandwidth is limited and power is limited. Distance turns every bit into an energy problem, because information must ride on photons that get diluted across space. Radio signals spread out as they travel, and intensity falls with the inverse square of distance. Double the distance and the received power drops by 4. At interstellar ranges, the drop is so large it dominates everything, and the link budget becomes the mission's heartbeat. Deep space network dishes can listen with extraordinary sensitivity. They still cannot pull unlimited data from a tiny transmitter across light years. The link budget becomes a wall of thermal noise and photon scarcity, where the receiver is counting faint fluctuations against a warm universe. To send more data, you can increase transmitter power. That demands more onboard energy generation and more waste heat rejection. Earlier chapters already priced that energy, and the bill returns here, because a stronger signal is also a hotter spacecraft. You can also increase antenna gain by making antennas larger. Large high-gain dishes are heavy and hard to point precisely. For a gram-scale sail probe, a large dish is impossible, and even for larger craft, the pointing requirements can dominate the attitude control design. Pointing accuracy becomes part of the bandwidth problem. A narrow beam improves gain, but it must be aimed. If the spacecraft cannot hold attitude, the beam misses Earth and the data is lost, not gradually but abruptly, like a flashlight slipping off a keyhole. Optical communication promises higher data rates with smaller apertures. Lasers can form tight beams which can beat radio in efficiency. The trade is brutal pointing requirements and vulnerability to misalignment, because the beam divergence can be measured in microradians. At interstellar distances, a laser beam is still a needle aimed at a moving target. Earth orbits the Sun moves through the galaxy, and the spacecraft moves too. The probe must predict where Earth will be years in advance, and it must keep predicting as its own trajectory estimate evolves. That prediction is not a single coordinate. It includes ephemerides, gravitational perturbations and uncertainties in the probe's own trajectory. A tiny prediction error becomes a miss measured in astronomical units, and the receiver sees nothing but darkness. Even if the beam is aimed correctly, the receiver must be ready. Earth-based receiving arrays must be maintained for decades. Institutional continuity becomes part of the communication system, because a transmitter that survives the journey still needs a listener that remembers to listen. Bandwidth limits reshape the science itself. You cannot stream everything, so you compress, prioritize, and discard. The probe becomes an editor of reality, deciding what is worth sending home and what will be lost forever in its onboard memory. That editorial role is another autonomy burden. The spacecraft must recognize rare events and keep the right data. It must avoid filling memory with noise while missing the one discovery the mission was built for, and it must do that without a scientist leaning over its shoulder. Compression helps, but it is not magic. Lossless compression is limited by the inherent entropy of the data, and lossy compression risks erasing subtle signals. When you're hunting for faint spectral lines or small brightness changes, the difference between efficient and destructive can be a single algorithmic choice. Pluto missions already show this trade in miniature. New Horizons stored data, then downlinked slowly for months. That was at billions of kilometers, with a functioning DSN and a healthy RTG, and even then the weight-tested patience. Scale that to light years, and months become decades. A probe might return only a thin trickle of images and spectra. The public expectation of high-definition exploration collides with physics, and the mission's triumph may arrive as a handful of carefully chosen frames. There is also a security and integrity problem. Long links are weak links, and weak links are error-prone. Error correction helps, but it consumes bandwidth and power, and it forces the mission to spend precious photons on redundancy instead of raw information. A corrupted packet at Pluto is a nuisance. A corrupted command at Proxima can be fatal if autonomy misinterprets it. Communication protocols must be robust against noise and against ambiguity, because the cost of misunderstanding is not a delay, it is the end. Now connect navigation and communication into one system. Navigation needs tracking data, and tracking data needs communication. If the link degrades, the spacecraft loses external updates, and must rely on onboard estimation, which means uncertainty can grow faster than confidence. That pushes autonomy from guidance into orbit determination itself. The spacecraft must decide when its state estimate is drifting. It must choose when to spend propellant to reduce uncertainty, and it must justify that choice with incomplete information. Propellant spent on correction is propellant not spent on attitude control and hazard response. Every burn is both a fix and a risk, because thrust errors and leaks exist. The mission becomes a continuous optimization under uncertainty, where the safest choice can still be wrong. For interstellar concepts that use beamed propulsion, communication and navigation become entangled with the beam. The sail must stay aligned to accelerate efficiently. If alignment fails, acceleration stops and the trajectory diverges, and the divergence may not be correctable later. The beam also becomes a potential communications channel. That sounds like a loophole, but it is still limited by pointing, distance and infrastructure. A beam powerful enough to push may be too precious to use casually, and it may not be available when the spacecraft most needs to talk. Deceleration concepts face the same control problem at the destination. Magnetic braking, stellar wind interaction, or a second beam all require precise geometry. If you miss the braking corridor, you do not get a second try, and the destination becomes a flyby you never planned. This is the deeper meaning of the two burns problem in navigation terms. Acceleration and deceleration are not just energy events. They are aiming events that must be executed with extreme precision, and they must remain consistent with everything the craft learns along the way. A flyby mission reduces braking needs, but it raises timing demands. At high speed, the encounter window is short. Instruments must point correctly, exposures must be scheduled, and data must be stored without human intervention, because there is no time to ask Earth what to do next. At relativistic flyby speeds, the target system is a brief flash. The spacecraft must decide what to look at first. It must handle unexpected brightness, dust and geometry in real time, and it must do so while its own sensors are being pushed to their limits. For a crewed mission, communication delay changes governance as well as operations. Earth cannot supervise daily choices. The crew becomes mission control, and mission control becomes a local culture, shaped by isolation and by the knowledge that advice arrives years late. That culture must manage risk without external arbitration. It must decide when to spend resources, when to accept exposure, and when to change plans. The ethical weight shifts on board because the authority is local, and because consequences cannot be exported back to Earth. For robotic missions, the ethical question becomes about trust in automation. We are asking code to act on behalf of a civilization, far from oversight. A mistake becomes permanent, and accountability becomes abstract, which raises an uncomfortable question about how much discretion we should ever grant a machine. So the navigation and communication barrier is not one technical gap. It is a coupled set of limits that grow with distance. Light time delay removes real-time control, and inverse square loss starves the data link, while tiny angular errors quietly inflate into cosmic misses. The result is a mission that must be self-reliant in perception, decision, and survival. It must steer through hazards, maintain its own health, and choose what story to send back. It must do this while the rest of humanity waits in the dark, watching a clock that measures years instead of minutes. This is where awe becomes a kind of humility. We have built machines that cross billions of kilometers and still whisper home. Interstellar travel asks for that same miracle, multiplied by 1 million and sustained for generations, and it asks us to accept that silence is the default state. Transition. With steering and communication constrained by light itself, the central question sharpens again. Are there any credible loopholes in physics, or only better engineering within the same rules? Next chapter, we stop looking at barriers one by one. We ask whether any proposed shortcut changes the price tag or only changes who pays it. Chapter 8 left us with a hard truth. Light time delay and weak signals force autonomy, and autonomy forces us to choose propulsion that can aim, survive, and finish. When commands take years to arrive, every decision must already be on board, encoded in software, sensors, and fallback rules. This chapter is the honest map of possibilities. It is not a catalogue of dreams, but a sorting line between known physics, extreme engineering, and ideas that quietly smuggle in miracles. Picture a workbench under harsh white light. Parts labelled, assumptions weighed, and every shortcut inspected for hidden impossibilities. Start with the temptation that keeps returning in every serious interstellar study. If onboard energy is too heavy, move the energy source off the spacecraft and push with light. The idea is old in spirit, reaching back to early solar cell proposals, yet it becomes newly sharp with modern lasers and microelectronics. Beam sail probes are the cleanest expression of that logic. A laser or microwave array stays near Earth, and a reflective sail turns photons into momentum. Photons have no rest mass, yet they carry momentum, and that momentum transfer, tiny per photon, adds up when the beam is intense. Miniaturization is the first reason this looks plausible. A gram-scale craft needs far less force to reach high acceleration, so the same beam buys more speed. Shrink the payload, and you shrink the required momentum change, which is why wafer-scale probes keep reappearing in design studies. The numbers still bite, but they bite differently. To push grams to a meaningful fraction of C, concepts reach for multi-gigawatt to terawatt-class beams. That is power on the scale of national grids, concentrated into a pencil-thin column that must remain coherent across immense distances. In the visuals, the array is not a single cannon-like laser. It is a field of emitters spread over kilometers, each one phase-locked so their waves add rather than cancel. The beam is built like a synthetic aperture, an optical instrument assembled from many smaller instruments acting as one. That beam must stay locked on a sail for minutes to hours. Pointing jitter, atmospheric distortion, and array phase control become mission-critical, not optional refinements. A microradian error sounds trivial, but over millions of kilometers it becomes a mist that slides the beam off the sail. Even the air above the array becomes part of the propulsion system. Turbulence bends light, so adaptive optics must constantly reshape the wavefront, using guide stars or artificial beacons as references. In a sense, the atmosphere becomes a shifting lens that the array must correct in real time. The sail is not a simple mirror. It must survive extreme photon flux without warping, shedding mass, or turning into a plasma that ruins reflectivity. At these intensities, absorption of even a small fraction becomes catastrophic, because absorbed power becomes heat that must be radiated away. A good sail is therefore a materials problem disguised as a propulsion problem. It needs high reflectivity at the beam wavelength, low aerial density, and thermal stability under violent gradients. The sail also needs a way to stay centered in the beam. Passive stability tricks, like shaping the sail, become as important as raw power. In close-up, imagine the sail as a shimmering film, thinner than a human hair, rippling under a pressure you could never feel with your hand. The pressure is gentle in everyday terms, yet over a large area it becomes a sustained push. The craft rides that push like a surfer on a wave, except the wave is made of light. Even if acceleration works, the two burns problem returns at the destination. A fast flyby is easy to imagine, but a useful encounter needs time, and time needs braking. The blunt truth is that arriving fast is not the same as arriving usefully, especially when targets are small and fleeting. Deceleration is the first major hurdle for starshot-like probes. Without braking, Proxima becomes a brief streak of data, and most targets become missed opportunities. At a significant fraction of C, the time spent near a planet is measured in minutes, and the geometry changes faster than instruments can calmly scan. A second beam at the destination is the cleanest braking mirror of the departure beam. It also demands a second civilization-scale laser array built years ahead. That requirement quietly turns a probe mission into a multi-decade infrastructure campaign, because the braking system must exist before the probe arrives. Photon braking using the destination star is another idea. You angle the sail to use starlight pressure as a brake, but the force is weak and geometry is unforgiving. Starlight is spread across space, and even close to a star the pressure is modest, so the sail must skim the system with exquisite precision. The sail must arrive with precise aim and orientation. A tiny angular error becomes a miss measured in astronomical units, and the braking opportunity vanishes. At interstellar distances, navigation is not steering by landmarks, but by faint star fields, pulsar timing, and constant self-correction. Magnetic sails offer a different braking path. A large loop generates a magnetic field that interacts with the interstellar medium, trading speed for drag over long distances. The concept is elegant because it uses what space already provides: thin plasma, charged particles, and magnetic coupling. The penalty is size and power. Effective magnetic braking implies kilometer-scale structures or strong fields, and both demand mass, deployment reliability, and long-lived power. The loop must unfurl without tearing, remain stable against micrometeoroid cuts, and hold current for years without maintenance. Magnetic braking also depends on a medium that is thin and variable. The local density and plasma conditions are not under our control, so braking performance carries uncertainty. The interstellar medium is not empty, but it is patchy, and its magnetic fields can twist and buffet a large magnetic structure. Carrying propellant for braking is the most straightforward solution. It is also the one the rocket equation punishes hardest, because braking propellant must be accelerated too. Every kilogram reserved for stopping is a kilogram that had to be pushed to cruising speed, which multiplies the cost of ambition. For small probes, carrying enough propellant to stop from relativistic speeds is nearly self-defeating. For crewed ships, it becomes a mass ratio that collapses payload. This is the tyranny of exponential growth. Each added requirement drags another requirement behind it, like a chain. So beamed sails trade onboard mass for external infrastructure. They move the bill from the spacecraft to the launch system, and the bill becomes an energy grid problem. Instead of a heavy engine, you build a heavy civilization capability, and you amortize it across many launches. A beamed sail era would require more than a laser. It needs power generation at unprecedented scale, thermal management for the array, adaptive optics, and governance to keep it funded. It also needs safety protocols because a misaimed beam is not a benign failure, but a high-energy hazard. There is historical precedent for this kind of shift. Radio telescopes grew from single dishes to interferometric networks, and GPS required a constellation and a global standard of time. Beamed propulsion would be another step in that tradition. Spaceflight as infrastructure, not as a one-off vehicle. It also needs a communications plan that matches the craft's size. A gram-scale probe cannot carry a high-gain dish, so downlink becomes the second major hurdle. The probe may be fast, but its voice is quiet, and distance turns quiet into near silence. Optical downlink from a tiny aperture is possible in principle. It demands extreme pointing, exquisite clocks, and Earth-side receiving arrays that can count scarce photons. In practice, the receiving system becomes a telescope network tuned for single photon statistics, pulling signal out of cosmic background. The link budget becomes a story of probabilities. Each photon is a messenger crossing light years, and most never hit the detector. So the probe must compress data, prioritize what matters, and transmit with error correction that assumes long gaps and occasional dropouts. The probe must also survive dust and radiation at high speed. At fractions of C, shielding is not a wall, it is a strategy of sacrificial layers and careful geometry. A grain of dust becomes a hypervelocity projectile, and even sparse interstellar particles can sandblast exposed surfaces over time. In the visuals, the craft's front edge is a blunt, dark wedge. It is not aerodynamic because there is no air, yet it is shaped like armor because impacts are the enemy. Behind it, delicate sensors hide in shadow, peeking out only when the risk is acceptable. Beamed sails therefore look like the most credible near-term interstellar probe pathway. They do not violate physics, but they demand infrastructure that looks like a new industry. The promise is speed for tiny payloads, and the price is a planet-scale commitment to precision energy. Now pivot to the approach that feels more familiar. Instead of pushing with distant light, carry your own power source and keep thrusting for months or years. This is the lineage of rockets and reactors, self-contained machines that do not depend on a beam remaining locked across space. Advanced nuclear and fusion roadmaps aim at sustained thrust without impossible propellant fractions. They promise higher exhaust velocity and longer burns, but they inherit heat and mass. In space, power is never just power. It is also waste heat that must go somewhere. Fission is proven, but high power to mass space reactors are not. A reactor that can run electric propulsion at extreme power must also reject waste heat through radiators. The reactor core can be compact, yet the radiators sprawl outward like wings, because radiation is a slow way to shed energy. Radiators are the quiet constraint that keeps returning. In vacuum, heat leaves only by radiation, so high power implies large area, structural mass, and vulnerability to impacts. The hotter you run them, the smaller they can be. But hotter materials are harder to build and harder to keep stable. There is a reason early nuclear electric concepts often look like skeletal insects. Long booms separate reactor and crew modules, and thin radiator panels fan out to glow in infrared. The ship becomes a thermal machine first, and a propulsion machine second. Nuclear thermal propulsion improves over chemical by raising exhaust velocity. It still cannot magic away braking, and it still must carry reaction mass, which compounds with mission speed. Heating hydrogen through a reactor is powerful, but the exhaust velocity is still far below what interstellar cruising demands. Nuclear electric propulsion can run for years with high efficiency. It is limited by power density, radiator mass, and the slow reality that low thrust needs long time. Ion engines sip propellant, but they push gently, and gentle pushes require patience and long-lived hardware. Fusion is the bigger promise and the bigger uncertainty. A fusion rocket needs sustained, controlled fusion, with a system light enough to fly and robust enough to run for years. Fusion offers far higher energy per unit mass than chemical fuels, yet turning that energy into directed thrust is the hard part. The breakthroughs are specific and brutal. We need ignition, or steady-state burn, high repetition rates, and conversion of fusion energy into directed exhaust without destroying the engine. Some concepts envision magnetic nozzles guiding charged fusion products, while others rely on heating propellant with fusion energy. We also need materials that survive neutron damage and thermal cycling. A fusion engine is not just a plasma problem, it is a lifetime of hardware problem. Neutrons embrittle metals and degrade superconductors, and the engine must endure this without a repair shop following behind. Even if fusion works on Earth, a spacecraft fusion reactor must be compact, reliable, and restartable. It must operate without a maintenance crew and without replacement parts. Space hardware already struggles with decades-long reliability, and fusion would demand that reliability at far higher internal stresses. Timelines are uncertain because the bottlenecks are coupled. Progress in confinement, materials, and power electronics must all arrive together, and each has its own pace. The history of propulsion is full of partial victories that did not combine into a flight-ready system until much later. If fusion becomes practical, it changes the map for fast Pluto missions first. It could enable higher delta-V with manageable propellant and shorten travel without beamed infrastructure. Pluto becomes a proving ground where autonomy, long-duration power, and deep space navigation can mature. For Proxima, fusion still faces the two burns problem. A ship that can accelerate to high speed must also decelerate, and deceleration is as expensive as departure. The symmetry is unforgiving. If you want to arrive gently, you must pay almost the same bill twice. One option is to accelerate halfway and brake halfway. That doubles the propulsion requirement, and it doubles the heat rejection and reliability burden across the whole mission. It also means the engine must run for years, then run again, after coasting through cold darkness and radiation. Another option is to accept a flyby. That reduces braking mass, but it forces instruments and autonomy to perform under extreme time compression at the destination. The probe must decide what to image, what to sample, and what to transmit, while the target system rushes past like scenery from a speeding train. A third option is to combine methods. A fusion ship could use magnetic braking near the destination, or a sail for braking, but integration adds complexity and failure modes. Hybrid designs can be powerful, yet each interface, between sail and hull, between magnets and structure, creates new ways to brake. Gravity assists are often invoked as a free trick. They are powerful inside planetary systems, but they do not create energy, and there is no convenient planet between stars. A slingshot steals orbital energy from a planet, and outside the solar system there is no prepared set of moving masses to steal from. Within the solar system, assists can still matter for Pluto. They can cut years, but they require alignment windows and accept higher arrival speeds that make capture harder. The trajectory becomes a negotiation with celestial mechanics, where a missed window can mean waiting a decade for the next. For interstellar missions, gravity assists become rare and marginal. The nearest stars are not placed to provide a chain of slingshots, and detours cost time and exposure. Every extra year is another year of radiation dose, micrometeoroid risk, and system aging. So the propulsion map splits into two categories: external energy concepts like beamed sails, and onboard energy concepts like nuclear and fusion, each with different invoices. One demands planetary infrastructure and exquisite pointing, while the other demands compact power and relentless thermal management. Now address braking again, because braking is where most optimistic timelines quietly fail. Any plan that reaches Proxima in decades must explain how it stops, or admit it will not. The difference between a visit and a glance is measured in delta-V, and delta-V is never free. Magnetic sails are attractive because they use the interstellar medium as reaction mass. They're also slow, and they demand large structures that must survive decades. The deceleration may be gentle, but it must begin far from the target, long before the destination star is more than a bright point. Photon braking is elegant because it uses the destination star. It is limited by the star's luminosity and by the sail's ability to survive close approach without tearing. Get too close and heat destroys the sail. Stay too far and the pressure is too weak to matter. Carrying propellant is reliable in principle. It is punished by mass ratio, and it turns the ship into a tank farm that must be accelerated, shielded, and cooled. Tanks add structure, plumbing, and failure modes, and they also demand long-term storage without leaks or boil-off. There is no free braking method. Every braking plan either requires external infrastructure, enormous deployed area, or propellant carried from home, and each choice reshapes the mission. The question becomes, which price can a real program pay, and which price only sounds cheap in a slide deck? Now shift from machines to people, because the central question includes biology. If we cannot go fast enough, we can change what within a lifetime means. The camera lingers on a human face in dim cabin light, because the distance is not only kilometers, but years. Suspended animation and hibernation are the first human-centered workaround. If metabolism can be reduced safely, mission duration becomes less psychologically and logistically crushing. Lower metabolism means less food, less oxygen processing, and less wear on the mind from endless routine. The engineering is not only medical. A hibernating crew still needs life support, monitoring, redundancy, and fault recovery, because a small failure can become fatal unnoticed. Sensors must watch for infection, organ stress, and equipment drift, and they must trigger interventions without panic or delay. There is also the problem of waking. A crew that emerges disoriented into an emergency is not a solution, it is a new hazard. So the ship must stage awakenings, test cognition, and verify that the world outside the pods is stable enough to face. Ethics arrives immediately. Consent must be meaningful across years of unconsciousness, and mission planners must define who can wake whom, and under what authority. If something goes wrong, does the ship wake everyone or only a subset? And who decides what counts as wrong? Radical life extension is the second workaround. If humans can remain healthy for centuries, travel time becomes less urgent, but the mission becomes a long governance problem. A voyage that lasts generations in calendar years becomes a single career, and that changes how power and responsibility accumulate. A long-lived crew must still endure radiation, isolation, and cumulative risk. Extending lifespan does not remove hazards, it stretches exposure unless shielding and speed improve. The body is not only aging, it is being slowly rewritten by cosmic rays and chronic stresses. Generation ships are the most extreme workaround. They accept that the mission is a moving habitat, and that arrival is an inheritance rather than a personal achievement. The ship is no longer a vehicle with passengers, but a world with citizens who have never seen Earth. This trades propulsion limits for civilization-scale design. The ship needs closed-loop ecology, durable manufacturing, education, conflict resolution, and a stable social contract. It must recycle air and water with near-perfect efficiency, and it must replace parts with onboard industry rather than shipments from home. Engineering and ethics entangle here. Children cannot consent to a mission they did not choose, and a society confined to a hull must prevent coercion becoming normal. What does freedom mean when the outside is vacuum and the nearest coastline is light years away? Reliability becomes cultural as well as technical. A generation ship must maintain knowledge, tools, and repair capacity for centuries, while its systems age under radiation. It must preserve not only machines, but the ability to understand machines, even as languages drift and priorities change. Even if propulsion was solved, the ship must still navigate and communicate across light years. It must keep its forward shielding aligned, and it must remain a functioning polity. Navigation becomes a slow, constant act of measurement. Star trackers, inertial systems, and periodic recalibration against the sky. These workarounds show the real shape of the barrier. When speed is expensive, we pay with time, and when time is long, we pay with institutions and ethics. The deeper question is whether our social technologies can become as reliable as our engines must be. Now draw the boundary line the documentary has promised to keep. Faster-than-light travel is not on this map as an engineering project because it is not just difficult. It is a different category of claim. one that collides with the structure of space-time as we have measured it. Warp drives and wormholes appear in equations under exotic assumptions. They require negative energy densities or forms of matter not known to exist in usable quantities. In plain terms, they ask for a kind of gravitational behaviour we have never learned to manufacture, store or control. Even when a metric is mathematically allowed, the energy scales are often astronomical. The proposals also raise causality problems that physics treats as warning signs. If a method permits closed time-like curves, it threatens the consistency of cause and effect, and that is not a small technical detail. So we keep the story grounded. The speed of light is not a challenge to be outsmarted with cleverness. It is a rule that shapes every mission architecture. It shapes how we communicate, how we navigate, how we plan failures, and how we define success. That does not mean the future is closed. It means progress comes from paying the price more efficiently, and from building the infrastructure to pay it at all. The most transformative advances may be incremental. Better materials, better power systems, better autonomy, stacked until they look like a revolution. For Pluto, the honest optimism is strong. Better nuclear power, higher efficiency propulsion, and improved autonomy can shorten trips, enable orbiters, and return richer data. Each mission teaches us how to run machines far from home, with weak sunlight and long delays. For Proxima, the honest optimism is narrower but real. Beamed sails could send tiny probes in decades, and fusion might someday move larger payloads, if heat and mass are solved. The first interstellar missions may look less like ships, and more like seeds, small, numerous, and designed to survive harsh odds. The climax is not a single breakthrough. It is the recognition that interstellar travel is a systems problem, where propulsion, shielding, navigation, and communication must mature together. A fast craft that cannot talk is a silent triumph, and a talkative craft that cannot survive is a brief signal followed by darkness. We began with a hook about distance feeling like imagination. The answer is that distance is an invoice, and the invoice is paid in energy, infrastructure, and time. The ore is real, but so is the accounting, and the future belongs to whoever can balance both. Transition. With the map drawn, the final question is no longer what is possible in principle. It is what kind of civilization chooses to build the machines, and to wait. The choice is technical, political, and philosophical at once, because the stars do not care how badly we want them. Next chapter we close the loop. We define what impossible really means, and what paying the price would change about us. We began with a simple hook, because the mind needs a handle before it can hold a distance. We have crossed space before, yet Pluto and Proxima still feel impossibly far, like names pinned to the dark. Now, we close the loop. Impossible here is not a ban on curiosity, it is a price tag. In engineering, every miracle has a receipt. Mass, power, time, and risk listed in unforgiving columns. The first line item is the rocket equation, a 19th century insight that still governs every launch. It links delta V to exhaust velocity and mass ratio, and it does so with a logarithm that hides an exponential punch. Add a little more required speed, and the propellant fraction swells until payload becomes the smallest fraction of the stack. In the launch footage, that reality is visible as towering tanks wrapped around a comparatively tiny spacecraft. Even when propellant is not the bottleneck, energy is. Kinetic energy scales with V squared, so doubling speed means quadrupling the energy you must supply. That energy is not abstract, because it must be generated, stored, and turned into momentum with real efficiencies. Waste heat follows behind like a shadow, and in vacuum the only way to shed it is by radiating it away. Then the bill doubles again, because arrival matters. If you want to stay, you must decelerate, and braking costs almost as much as departure. A flyby can spend all its energy budget on getting there, but an orbiter must also pay to match velocities. That is why gravity assists are so prized. They are nature's way of moving the decimal point without burning propellant. This is why Pluto is reachable but still hard. A probe can fly by, but orbit and long operations demand extra delta V, power, and mass. Pluto's gravity is weak, so capture requires either a large braking maneuver or clever techniques that add complexity. Every additional kilogram of propellant also demands stronger structures and larger tanks, and the spiral continues. New Horizons proved the point by design. It arrived fast, took its data, and kept going, because stopping would have rewritten the entire mission. The spacecraft was built like a sprinter, not a camper, optimized for a brief, precise encounter at extreme range. In the images, Pluto swells from a pale dot to a world with glaciers and haze, and then it begins to shrink again. Pluto also punishes patience with weak sunlight and long delays. Power falls with distance, bandwidth collapses, and every decision must be planned far ahead. Solar panels that work near Earth become impractically large, so deep missions lean on radioisotope power and strict energy budgets. Even then, data returns arrive slowly, parceled out over months because a distant transmitter is whispering across billions of kilometers. Proxima is not Pluto scaled up. It is a category change, because light years turn mission engineering into civilization infrastructure. The numbers stop fitting into familiar intuition, and they start rewriting what mission even means. When the destination is 4+ light years away, the journey becomes an era. To reach Proxima within a human lifetime, you need a leap in propulsion. Chemical rockets imply millennia, and even advanced onboard systems face brutal mass and heat limits. High specific impulse helps, but it often comes with low thrust, so travel time and power supply become entangled. The faster you want to go, the more your spacecraft begins to resemble a power plant with a payload attached. Beamed sails move the energy source off the craft, but they move the program onto Earth. The required power, optics, and pointing become grid scale and governance scale. A laser array would have to hold a beam on a tiny sail across vast distances, correcting for turbulence and Earth's rotation with exquisite phase control. In visual terms, it is a planet-sized instrument trying to thread a needle in the sky, and the two burns problem returns at the destination. Without a braking method, Proxima is a brief flyby, not a visit with time to learn. At a significant fraction of light speed, the target system flashes past in hours or days, not years. You can take pictures, maybe sample fields and dust, and then you're gone, still moving into the interstellar dark. Human limits tighten the definition of impossible. Long missions demand shielding, closed-loop life support, reliability across decades, and psychology that does not fracture. Biology does not pause just because a spacecraft is well designed, and time is not negotiable. The longer the voyage, the more the mission becomes a moving ecosystem that must stay stable without resupply. Radiation is not a background detail. It is cumulative damage to bodies and electronics, with solar storms and cosmic rays setting hard exposure budgets. Beyond Earth's magnetic field, high-energy particles can break DNA, degrade materials, and flip bits in memory. Shielding helps, but shielding is mass, and mass is propulsion cost, so the trade is never clean. Dust is not romantic either. At high speed, sparse grains become impacts, and shielding becomes mass you must accelerate and then decelerate. A grain the size of sand can carry the energy of a bullet when relative velocities are extreme. Even at Pluto, micrometeoroids are a concern, and at interstellar speeds they become a defining hazard. Navigation and communication add a final, non-negotiable constraint. Small angular errors grow with distance, and light speed delay removes real-time control. A tiny pointing mistake early in the flight can become millions of kilometers at arrival, like a compass error that widens into an ocean. Autonomy is not a luxury out there, because the spacecraft must think while Earth waits. At Pluto, the delay is hours, and the deep space network can still pull whispers from noise. At Proxima, a message takes years, and bandwidth becomes a trickle. The inverse square law punishes radio links just as it punishes sunlight, and the receiving antennas must work at the edge of detectability. In practice, communication becomes less like conversation and more like archaeology. So what does impossible mean precisely? It means not forbidden by physics to send something, but unreachable for humans within practical budgets, timelines, and risk tolerance today. It also means the margin for error collapses, because the distance magnifies every weakness in design and planning. The universe is not saying no, but it is demanding proof. It also means probes are possible, but only with severe trade-offs. Tiny payloads, limited data return, extreme autonomy, and acceptance that many attempts may fail. You may choose grams instead of tons, redundancy instead of comfort, and statistics instead of certainty. The question becomes uncomfortable and clarifying. What is the smallest machine that can still do real science? This answers the central comparison. Pluto is a hard mission problem, especially for orbit and endurance. Proxima is a civilization problem, demanding new propulsion and sustained infrastructure. One can be tackled by a determined agency and a patient public, while the other asks for decades of coordinated capability. Transition. With the barriers synthesized, the future stops being a fantasy and becomes a roadmap. The point is not to shrink the distance with optimism, but to reduce the unknowns with disciplined steps. The near-term path is not a starship. It is faster outer solar system missions that prove high-power propulsion, deep autonomy, and long-lived systems. It is trajectories that cut travel times, instruments that survive the cold, and operations that function when the sun is only a bright star. Each mission becomes a rehearsal for remoteness. It is nuclear electric demonstrators that run for years, not weeks. It is thermal management that works in vacuum, and radiation-hard computing that stays trustworthy. Long-duration testing matters because deep space punishes the gap between a laboratory hour and a mission decade. Reliability is not a feature, it is the mission. It is beamed energy experiments that scale honestly. Better phase control, better sails, better pointing, and safety frameworks that treat the beam as critical infrastructure. The physics can be tested in pieces, but the system must eventually work as one coherent machine. If the beam wobbles, the sail misses, and the dream becomes a missed distance. It is deep space operations that assume delay, spacecraft that diagnose themselves, prioritize science on board, and survive without constant human correction. That means fault protection that is conservative but not paralyzing, and onboard planning that can adapt when the unexpected happens. In a sense, we are teaching machines to be explorers. Each step moves the frontier without pretending the barrier is already broken. Each step turns impossible into expensive, and then into funded. The history of exploration is full of these transitions, where a concept becomes a prototype, and a prototype becomes an institution. In the end, the distances are not an insult to ambition. They are a truth we must honour because they define what it means to leave home. When you look at a star field, you are seeing both invitation and constraint, beauty with a cost. If we cannot reach Proxima soon, the attempt still changes us. It reshapes power systems, materials, autonomy, and the science of living off Earth. It forces clearer thinking about risk, about stewardship, and about what we value enough to sustain across generations. And it returns us to a quieter awe. Our greatest achievement may be learning to live wisely in our solar system, while building tools that one day make the stars reachable. Not closer, not smaller, but finally within the range of what we can do on purpose. Across this journey, we learned that space only looks small on screens, because our maps erase the long dark where time, delay, and drift become the plot. Pluto taught the lesson with brutal clarity. Even our fastest probe arrived as a fleeting flyby, because stopping costs nearly as much as going. Underneath every mission sits the same compounding framework: delta V budgets that trigger the rocket equation, energy that rises with speed squared, power and waste heat that must be carried or rejected, and hazards that accumulate while the calendar keeps moving. When propulsion gets more efficient, thrust often collapses. When thrust returns, the power plant swells, and the payload shrinks into an afterthought. Radiation and dust turn high speed into impact energy, while shielding adds mass that demands more energy, and the loop tightens again. Communication is not a convenience but a law. Inverse square losses and light time delay force autonomy, and autonomy must survive decades of aging hardware without a human hand. By the time we scale from light hours to light years, the problem stops being a single vehicle and becomes a coupled system of propulsion, braking, protection, navigation, and institutions willing to wait. The honest map of possibilities showed no loophole that lets us smuggle in miracles, only architectures that move the bill around: nuclear electric for patient thrust, beamed sails for offloaded energy, and clever braking ideas that still demand precision, infrastructure, and risk tolerance. In the end, impossible wasn't a verdict on imagination. It was the current total on a receipt written in mass, power, heat, time, and governance. And yet the receipt also revealed something hopeful, because every line item is measurable, and anything measurable can be engineered, if we decide it matters enough. What was stopping us then? Physics, fuel, fragile bodies, or engineering? And what breakthrough would finally make the impossible a flight plan? It was never one villain, but the way the limits multiply. The rocket equation punishes propellant, energy punishes speed, braking doubles the demand, biology punishes exposure, and light itself punishes control. The breakthroughs that could change the story are not a single magic engine, but a synchronized leap. High-density power without crushing mass, thermal rejection that scales, shielding or mitigation that doesn't bankrupt Delta V, autonomy that can steer and self-repair in deep time, and a credible way to solve the two burns problem so arrival is more than a blur. So perhaps the better question is not whether Pluto or Proxima are too far, but whether we are willing to become the kind of civilization that pays for arrival, not just departure. The distance is real, but the deeper challenge is choosing patience, building infrastructure, and accepting that the first true interstellar craft will be as much a social project as a machine. If this story leaves you with one task, let it be this: learn the price tags, support the incremental tests that retire them, and keep demanding plans that add up, because that is how impossible becomes scheduled. What was stopping us then? Physics, fuel, fragile bodies, or engineering? And what breakthrough would finally make the impossible a flight plan? It was never one villain, but the way the limits multiply. The rocket equation punishes propellant, energy punishes speed, braking doubles the demand, biology punishes exposure, and light itself punishes control. The breakthroughs that could change the story are not a single magic engine, but a synchronized leap. High-density power without crushing mass, thermal rejection that scales, shielding or mitigation that doesn't bankrupt Delta V, autonomy that can steer and self-repair in deep time, and a credible way to solve the two burns problem so arrival is more than a blur. So perhaps the better question is not whether Pluto or Proxima are too far, but whether we are willing to become the kind of civilization that pays for arrival, not just departure. The distance is real, but the deeper challenge is choosing patience, building infrastructure, and accepting that the first true interstellar craft will be as much a social project as a machine.